C'est envoyé la même chose aux deux télés, là. Il y en a une qui coupe et pas l'autre à un moment. Yes. T'arrives à quelle heure les gens? On sait pas. Je croyais que ça commençait à 9h15. Donc, je parle des gens que je dois équiper. Je vais demander à Thomas. Bonjour. Hein. Oh. C'est quoi le problème, JC?
Pardon?
Qu'est-ce que tu baragouines encore?
Peut-être ça aurait été mieux si vous avez passé le câble au ras, tu sais. Là, ça marche le micro. Plutôt que de passer au-dessus des accoudoirs, tu aurais pu passer dessous, tu sais. Comme ça, on se prend pas les pieds dedans. En fait, c'est sur toute la longueur, sur chaque travée, tu sais, ça passe au-dessus, à chaque fois, ça traverse.
Est-ce que tu m'entends? Je te parle. Tu m'entends ou pas? Ouais. Ok, bah je mute. Test 1, 2, 3.
Ok, ok, le micro marche. Attends, ça fait un peu d'écho, c'est bon? Ok, let's start. So, welcome in this new Dpdk summit in Arcachon. So as you know, it's not a news. We got 3 years of COVID without any in-person summit, and now we meet again. There is a limited in-person attendance because travels are limited for various reasons. So that's why we will have a lot of attendees on Zoom and YouTube streaming. So, as a consequence, that's the first hybrid Dpdk event in the history. Nathan, you want to present yourself?
Good morning. My name is Nathan Southern. I'm project coordinator for Dbdk Linux Foundation, and I'm very happy to be here. Should I say a few words now? My background is not in tech. It's in stakeholder and communications management, and I've only been on the project for a short time, about 5 months. But during that time, I've learned a lot, and one of the things that struck me in the beginning, and Dbdk is a project that I'm on of 3 with the longest lifespan. It's been around about 12 and a half years, and one of the things that struck me is just how much recognition it has. I went to the Linux Foundation All Hands in Scottsdale, Arizona in May, and when I talked to Linux Foundation executives, members of the LF community, that was the project. When they asked me, what are you working on, that was the project that got the most recognition. That was the one they wanted to talk about. And my other 2 projects are also very vibrant, and they're much younger. And I talked to our chair, Jim St. Ledger, and mentioned this to him, and he said, the reason is that Dpdk is an industry standard. It's a stalwart. It's been around a long time, and it's an incredible success just from an ROI standpoint. Everybody in networking has heard of it. And that's definitely true, but I think I've seen something even deeper just from talking to Jim and also being here yesterday, which is that there's a deeper reason for the project's ongoing success, and that's you guys. That's the community. Just the vibrancy of your contributions and the capacity for debate and insight and sharing end user stories of personal experiences. That's really what makes this project unique and special. I think we face a couple of real key challenges here. One is that we are transitioning to another chair, and those shoes are going to be very difficult to fill from the standpoint of leadership. And the other challenge is just a challenge that all projects face, but particularly pertinent in the case of Dpdk, which is post-pandemic. The nature of community is changing. We're shifting from an environment where conferences are all in-person to a more hybrid environment where we're seeing more virtual participation. And I'm confident we can rise above and each of those challenges and continue to be a great success. But that's really going to depend on you guys. To continue to foster debate and community participation even across virtual barriers. I'm looking forward to seeing that happen. I think we saw the seeds of it yesterday, and I'm confident that this conference will continue that. So thank you very much.
Thank you, Nathan. Welcome. And so you'll be the animator in the room for these 2 days.
Yes.
Thank you. Few more words about Dbdk. So now we move to a pace of 3 releases per year. And each year we are doing some miracle features, hundreds of contributors, etc. Thank you, everybody. A quick look of how it looks now. You see there are a whole lot of companies contributing. Now we see that more and more companies are contributing, and the part of each contribution looks more and more balanced. Few words. First, yes, we are doing 3 releases per year. for the main branch. We are doing also some releases on the LTS branches. And for all these releases, we still need more validation. So please, if you can help to do some tests on your behalf and just reply to the release emails, it will help a lot. And another thing, we need more people to be informed in case of CV fixes. You need to be informed in advance, and for that, you need to ask to be registered in the mailing list security pre-release at dpdk.org. Because yes, that's a fact, we are seeing more and more vulnerabilities that we are fixing. So let's work on this. Now, about this event, so you all have the Wi-Fi access for those who are on site. For those who are remote, you can use Zoom or the YouTube. It's streaming as well. But on Zoom, you can ask questions, chat, etc. And all the slides are on skate.com, or should be. Because yes, all speakers today and tomorrow have to upload their PDF in advance, if possible, on skate.com. And please give time to questions. That's a very important part of this event. We want to make it very interactive. And don't hesitate to ask questions, of course. For a speaker here on site, try to be ready in advance. You need to get a microphone, etc. We can check everything during the breaks. For people who are remote, you need to join a specific Zoom channel that you have the link, and you need to check your audio video is working, etc. Let's try to make the experience very good. Again, for those who are on site, you can enjoy some breaks and some lunch on the ground floor. Please make your phone silent. Don't bring food and drink or even smoke in the auditorium, of course. This is the full schedule. We are going to start. We have a very great lineup this year again. So ask questions. It needs to be very interactive. Raise your hand. You can write on Zoom, you can write some questions as well. And follow the code of conduct from the Linux Foundation, please. Okay? Enjoy this summit. Thank you. So this morning we'll start with a few virtual presentations.
Hi,
Okay.
my name is Rsa, and in this presentation, I'm going to talk about virtualization of Dpdk applications using Vhost Vhost User. We will start with a brief introduction of Vhost User and go through a couple of example configurations of how Vhost User can be set up. We'll go through a use case where virtualizing Vhost User applications can be beneficial and what the possible advantages are of doing so. After that, we can go over a potential method for virtualizing Vhost User applications through a device called Vhost Vhost User, or VVU for short, as well as go through how some of the Vhost messages are handled by VVU to just get a better understanding of how it would work. We can finish off then with the current status and the possible next steps for VVU. We begin with a quick introduction to Vhost. So Vhost is a message-based protocol that allows the hypervisor to offload the data plane to either the kernel, in which case it's called Vhostnet, or the user space where it's called Vhost User. In this presentation, the focus is only going to be on Vhost User. The diagram on the slide shows a simple example of forwarding packets between the guest VM, which is also called the front end, to somewhere external, for example, the internet. We do this through the Dbdk test PMD application with the Vhost user module, which is also called the backend. So using Vhost, the front end sends the hypervisor's memory layout so that the backend can locate the work queues and the buffers within the hypervisor's memory space. And the front end also sends a pair of file descriptors for the backend to send and receive notifications. The main advantage of using Vhost is that the hypervisor will no longer process packets, so it won't do reads or writes to and from word queues. Instead, the data plane will be completely offloaded to the vhost user, so which can now access the word queues memory regions directly, as well as send and receive notifications to and from the guest. The diagram in the slide shows how the Vhost user module in Dbdk can also be used to forward packets between two virtual machines. The interaction between the guest VM and the Vhost user module is similar to what was seen in the previous slide. This type of setup is often seen in NFVs or network function virtualization architectures, where virtual machines are deployed to deliver network functions. For example, the guest VMs in the slide could either represent a router or a firewall or a load balancer, forwarding packets to another virtual network function. So the question is, why do we actually need to virtualize the Dpdk applications that use vhost user? So as seen in the previous slides, the current implementation creates a host user space process that acts as an intermediate for inter-VM communication and for external packet forwarding. The state of user space processes can't be saved and restored, which can be an issue during host kernel live update. Host kernel live update is as it sounds. You first create a snapshot of the guest VMs running on your server and then save the snapshots. The host reboots into the new kernel, at which point all user space processes are terminated, including the Dpdk application. And then finally, the guest VMs are resumed from the snapshots after the updated host kernel has booted. During this process, low downtime is essential for guest VMs that are working with low latency applications. For example, those used in networking and machine learning. In the existing implementation, restarting vhost user application after the host boots into the new kernel and bringing that Dpdk application back to the state it was before the reboot can be quite a time-consuming process, adding much more to the downtime of guest VMs. On the other hand, as we will see in the next few slides, when the Dbdk application is moved inside a VM, the VM can be snapshotted and the state of the Dbdk application can be saved and restored quite quickly, resulting in much lower downtime. Another possible advantage of virtualizing vhost user applications, as we will see later, is that it also allows secure and direct VM to VM communication without using an intermediate host user space process. This I believe can be more desirable for cloud providers where most software is run in isolation in either containers or VMs and not as host user space processes. So it does provide a security benefit as well. Before moving on to the design details of how we virtualize the vhost user backend, I wanted to point out the previous work that has been done to establish the direct VM to VM communication without a host user space process. So one of the initial work was called Vhost PCI, which needed a different kernel driver for each device. So Vhost PCI block for block devices, Vhost PCI SCSI for SCSI devices, and so on. And this was one of its drawbacks, and it was never merged upstream. After that, Stefan from Red Hat then proposed a VirtIO vhost user, or VVU, which is a single VirtIO device type that exposes the vhost user protocol to the driver instead of a family of new VirtIO devices that Vhost PCI exposed. And this is what we will use for virtualizing vhost user backend. So let's get into the working of VirtIO vhost user. This slide has a lot going on in it, but I think it's important to show what changes happen when we move the Dbdk application inside a VM. So on the left hand side is the diagram from the introduction slide we saw earlier, where you have a guest VM, the front end, which is forwarding packets externally through vhost user library in Dbdk, which is the backend. On the right hand side, we are using Word.io Vhost user. So what we have done is we have moved the Dpdk application to inside a VM. The good news is that this does not require any change on the front-end side. It's still Word.io on a device connected to a Unix socket, sending Vhost user protocol messages, both the left and the right diagrams. All the changes that happen are in the backend. In the existing Vhost user implementation, on the left-hand side, we can see that Dpdk directly sends and receives messages via the Unix socket. When we move the Dbdk application inside the VM, we have a VVU PCI device in the hypervisor that acts as an Dbdk and the Unix socket. So the big change in Dbdk is that it's now interacting with the VVU PCI device that has been directly assigned to user space via VFIO, rather than interacting with a Unix socket. So the major change in the overall design now is that the backend is now split into the backend device in the hypervisor and the backend driver in Dpdk. And in the next few slides, we'll have a much deeper look into how the backend works. So as seen in the backend figure on the slide, the main method via which the VVU device and the Dpdk driver interact is via word queue for forwarding the Vhost user messages that were passed and by the device and sending a reply from the driver to the device and then to the Unix socket. And the second method is via a PCI bar for notifications and for memory sharing with the front end. Whenever the VVU config changes, for example, when the device wants to notify the driver that the Unix socket has connected or disconnected, this happens via a Word.io config change interrupt. And the device finds out that the driver is ready to accept messages using writes by region in the device. There are currently around 40 different types of Vhost messages that we can send from the front end to the back end. I wanted to go over how 3 of these messages are handled by the backend, which should hopefully give a good understanding of how the different parts of VVU device and driver work. So we start on the slide with a relatively simple message, Vhost user get features, which is sent by the front end to get the protocol feature bits before the feature negotiation between the front end and the back end starts. Only the word queue is involved in this message, and the PCI bar is not used. So in step 1, as with all Vhost messages, the Vhost is received. The message is received by the VVU device through the Vhost user Unix socket from the front end. The device in QEMU passes the message and puts it on the RX queue for the Dpdk driver to read. After receiving the message, the Dbdk driver sees that it was a Vhost user get message and adds the features it supports to the message payload, and it sends it in the reply on the TX queue to the device. And then finally, the device passes the reply and forwards it back to the Unix socket. So this is quite a simple message, and it doesn't require the use of PCI bar. Next, I wanted to look at Vhost user setmem table. This message is used by the front end to set the memory map regions on the backend so that it can translate the VRENG addresses. The backend uses both the word queue and the PCI bar for this. So in the first step, similar to other Vhost user messages, the message is received by the VVU device from the Vhost user socket. And in the ancillary data, there is an array of file descriptors for each memory map region that the front end wants mapped. In the second step, the device then maps each of these Vhost memory regions into its own address space using mmap. And in order for the driver to write to these mmap regions, the VVU device then initializes a RAM device for each region from the mmap addresses. So access to these RAM devices modifies the memory directly, right? The RAM devices are added as subregion to the PCI bar of the VFIO PCI device. Therefore, writes by the driver to the PCI bar are directly reflected on the front end. In step 4, the VVU device puts the message on the RX queue for the Dpdk driver to read, and finally the Dpdk driver then saves the information so that it can translate the viewing addresses in the PCI bar. Finally, I wanted to look at vhost user set variant call. This message is used by the front end to set the event file descriptors to signal when the buffers are used by the backend. Similarly, the first step is the same as the previous messages. The message is received from the vhost user socket. The ancillary data of the message of the message from the character device contains the file descriptor to set when the buffers are used. In the second step, the VVU device registers a doorbell. So it's called a device auxiliary notification within the PCI bar, so that when the driver writes to that doorbell region, the device triggers the event FD. The device then puts the message on RX queue for the Dbdk driver to read and realize that it is a vhost user set variant call. The Dbdk driver then saves the information in its word queue call FD, and later on, when the buffers are used and the Dbdk driver wants to trigger the event FD, it writes to the doorbell register for the specific word queue. Now, I think the three messages show well how the three messages show well how VVU works, and I think now we can look at the downtime for host kernel live update with and without virtualization. In both these cases, the host and the front end were kept exactly the same. Only the backend was changed from the existing host user space implementation to VVU implementation. Without virtualization, the Dbdk application is run in climb mode. This is important so that it can reconnect back with the guest VM after the reboot. The downtime for existing vhost user implementation is just over a second, while the downtime for virtualized implementation is just under half a second. So using VVU, the downtime improved by approximately 55%, which is quite significant. As for the work currently being done for VVU, the virtualized implementation requires changes in the VirtIO spec to introduce the VVU device, as well as introduce new VirtIO device resources to send notifications from driver to device and vice versa, which are not of buffer used or buffer available notifications. The V2 version of the patch is currently in review, and it can be found on the link in the slide, along with the VirtIO spec with the change. The instructions to build and run a working prototype for VVU can also be found on the GitHub link on the slide. The next steps are to get feedback on this design and to further discuss the changes required for VVU on the VirtIO mailing list. And if the upstream community is happy with the approach, we can start sending the patches for QEMU and Dpdk for the VVU device and driver respectively. Thank you.
Vhost user live upgrade optimization, and he's with ByteDance. I
I can't really, I didn't really hear the question. Sorry about that. Sorry. The the voice is quite low. No, not really. No, just a little bit. So,
Okay, so if there is no question, we have 15 minutes before the next talk. So I suggest maybe to have a short break.
Sounds good.
Okay, thank you.
Hi, I'm not sure what's happened. I thought I heard a question, but then I couldn't.
Okay, ready for our second speaker. This is Jihong Wang from ByteDance. He'll be talking about Vhost user live upgrade optimization. And again, I would encourage everyone, both in the audience physically here and virtually, who's zooming in to go ahead and post questions during Jihong's talk in the chat, and we'll come around to them at the end, and we'll so that you guys can engage them in some Q&A. Thank you.
Hi, hello. Can you hear my voice? Okay. Hi, I'm Dihong from ByteDance, and let me share my desktop. Okay. Sorry. Sorry, just a little bit. Since I cannot share. Is there any way I can set my size and you can share for me? Okay. Let me try first. Okay. Okay. How about now? Can you see my screen here now? Okay. Thanks. Sorry about that. Sorry for the 5 minutes now. So I'll try to keep the pace. Yeah, I'm Zihong, and you can see Nian also, and you will see Nian later on the stage, I guess. So this topic is about the virtual switch upgrade, which is actually a ancient topic. I mean, during the years, people have proved that there are many ways to do that, and today we're going to share our way to optimize that. And so here is the content. First, we're going to some quick background introduction like why did we do this, right? Is it really necessary to do this? And then we will share all the details. Okay, let's get started. First, some quick background. So first of all, nowadays that we know there's a lot of offload. There's quite a few offload solutions already, and but they're good and they have good performance. And in the meantime, the software virtual switch still has its unique merits, such as it's stable, it's out of the box, and for the agility, we can easily to develop some features, and also the performance. We need to mention is it's also increasing during the years. They have good enough performance to cover quite a lot of scenarios. So another background is about the Vhost user. This part that I'm going to just quickly talk about, like the Virtual, we know the Virtual Net. It has some like all enough basic features we need, and it also has a lot of features for example like migration. It has good support there, and also the performance of it. We have seen performance improvement during the years, such as first of all, the CPU is running faster, and also we can do like macro architecture level optimization there, especially for memory copy, like for different architectures, and also like there are different other technologies coming, like the DMA engines, those stuff. They're in the community right now. So all this suggests that software virtual switch still can cover a lot of scenarios, and sometimes they have just the good TCO there, and just to ensure we can meet all the good stuff we just mentioned, such as agility and good to maintain and those stuff. We really need the rapid iterative development model. So to make sure of that, upgrade is really necessary. It's almost mandatory. So when we start to design the upgrade solution, the objective is very simple. So first of all, it's going to be really, really reliable, because that's a bottom line, right? Like it's going to be able to run like millions of times correctly and handle various situations. And then secondly, it need to be guest unaware. That's also very important, because we're really gonna run that. There's gonna be tens of thousands of servers, and if we cannot do the next thing otherwise, if every time we do an upgrade, the guest will see a network card down and up, and the network blackout for several seconds, that's going to be a total disaster. So the second is going to be guest unaware, and then of course it's going to be flexible. That's why we do upgrade, is to allow necessary changes to different part of the program. So that's 3 parts. And to just talk a little bit about the process, the path we choose is to do process iteration, which means when we have an old process running, and then we start the new process by side, and then we just sync and transfer everything needed from the old process to the new one, and then the new one can take over, and the old one can quit. So just list a few here, like the sessions and also the data path. The sessions they can do in parallel, like the old ones can still be functioning, and then we can sync the sessions just in the meantime. And for the lead card, the data traffic from the file, we can that we can use VFs, or we can use like traffic duplication. Those technologies can solve that part, but one part of that is a little bit tricky, which is the data path between Vhost and the virtual machines, QEMU and the virtual driver. Of course, we naturally we can just disconnect. The old one can quit, and then the new one can start talking to the kernel, and everything, just redo the negotiation process. Everything goes back normally. But that one, as we showed here, it's a little bit time consuming, and so obviously this one is quite reliable. This process is very reliable. Basically, they reduce all the negotiation process, and this one is also flexible. Basically, the old one does not need to care about the new process, but the downtime is a bit unbearable. We can, and here is the number we showed. Like we tried from tens to hundreds of reports. The total downtime can be like 2 to 5 seconds. So if it's just one time, then it's okay. But if we do this from time to time and to like hundreds of thousands of servers, that's going to be unacceptable. Okay. So naturally, we try to optimize the downtime, and to make sure that the guest is unaware. Basically, we can the way we can think is that make the just to take out the renegotiation process. Like if you just keep the because between the virtual and the host, it shares all the memory stack and also the FDs, right? And just to make sure that the new process can also have those information, and then you can rebuild the connection, and then just the kernel doesn't even notice that anything changes in the backend. So and this is very simple idea, and not just applies to the Vhost, but in a lot of other different scenarios. That one we can probably see that it's also been leveraged there. And for Vhost Builder, what we need to transfer is the devices and also the sockets, just to make sure that the FD connection does not break out, and also the new process can just leverage all the verticals to continue to talk with the QEMU, the driver. And basically, this is all simple engineering work. No need to go to all the details, but just one thing to want to call out here is we need to make sure the handover process very smooth, and to make sure of that, we need to make sure there's only a single operator at one time. For example, the message handling. So just to make sure that we, when we start the migration process, the old one will stop the message handling nicely, and then just do all the transfer and just to make sure that the message handling happens only at one side. Okay, and also is the data path. So we can go to the next. Let's first talk about the message handling part. What we can control is when we do the upgrade, is that we can say, oh, we don't add new ports, and we don't do other like maintenance stuff. But what we cannot control is what the guest will do, right? Now the guest can say, I'm going to change the queue numbers, and also maybe the guest will try to restart, or just pull out the driver and insert another driver. So there's going to be a message flow between the host and the QEMU. And in that case, we need to make sure, no matter what the situation is, like there's message handling ongoing, but when we try to do that, the upgrade, we needed to first pause the message handling in the old process, and also the new process need to make sure the message, just to make sure it has a clean state to accept all the transfer, and the old one should create the spread nicely. That so make sure that once it receives the message, it will handle that before it create. And then after everything is done, the message handling can be resumed. And if the process is done nicely, then the new process can just call the function to start the process. But if it fails, the old process can just resume the message handling and pretend nothing just happened. So if we want to try again, then it's okay to restart the process. And then there could be exceptions. Most of them should be like, in some cases, the devices are in faulty state. For example, sometimes the negotiation process breakdown, maybe because of the driver, maybe because QEMU, some other different causes, but there could be. So what we need to do is to really check all the devices before we do the migration, and skip those in faulty state. And for anything else, we can just cancel the transfer. This process may look a little bit complex, but really, if there's anything go wrong, we just need to cancel the transfer and do nothing else dramatic, because the old process is still running, and the transfer just happens. It's not mangling with the data path, so it's just a transfer process, and it's easy, and it's okay to just cancel that. And we have run this like millions of times, but maybe I can just recall maybe 1 or 2 times it's caused by socket failure, but there should be no other things that's caused the failure. And this solution looks very, very reliable. Okay, so let's talk about the downtime, because the way why we do this is to really to trying to minimize the downtime. So just a few tips here, and this is what we learned during the process. First is we only need to stop for the volatiles, which means the indexes, and everything else we can just pre-copy them, just treat them as sessions and other static stuff, because once you stop persisting the message, then everything becomes static except for the data path. So and we need to notice that the devices and other sockets, they are huge if you have many ports there. So it takes a lot of time. We can just do the pre-copy, and then make sure the switch happens. The data path switch happens when everything else is ready. We don't need to wait for other information to be ready, such as the NIC, maybe the VTAP or other information. that one can, because once we stop the old PMB in the old process, the network downtime start coming. So that's also some straightforward idea. And then third is to avoid the CPU contagion. Basically, when we have two processes designed for the upgrade, we have double copies for like memory, but for CPU, definitely we're going to need only have one, the same PMD. So that makes sure the new process does not start the PMB, before the old one stop. Otherwise, no matter which one is persistent traffic, if you run two PMDs on the same core, you will experience like tens of milliseconds of jitters, and that one can make the guest notice. That jitter is almost higher than the actual downtime of the upgrade itself. And finally, it's suggested to use automated state machine, not use a lot of commands to do the whole process. The state machine can for example, we can show in the process like this is like the state machine, and the blue one are the old process, and the green boxes are new steps in the new process if we use this state migration mechanism. And if we start counting from the old one PMD stops, and all the way to until the new process starts this PMD. Now this is the time period that the network pause. It's not like network down, because the queues are still functioning. The guest can still update the indexes and send packets, but at this time there's no packet persisting in the host. So we need to make sure that every microseconds here counts. So just make sure that it has a very, very tight state machine here. Once we stop the PMD and we sync the final volatile indexes, those states, and then in the new process we just attach the PMD and we can start the message handling, and then we can fabricate the flow from leak. And finally, we can start the PMD. And then this picture shows, let me see how many times we have. Okay. And this picture shows the time breakdown of we have two sets of environment. One is like 18 ports, and one is like 255 V ports. But we can see that almost no other feeds they stay the same, but when we have more vhost port, the final state sync process, which is here, like it increases a lot, and also the vhost PMD config. This part also start to increase when we have more vhost port, but the others they almost stay the same. And now the numbers here is microseconds. So although it looks like when we have more vhost port, the time has increased a lot, but if you compare with the old ones, like the second stable, this one is still very very good looks. And also we didn't do any dramatic optimization here, because for the state migration, the reliability is a key objective, and the mechanism itself is a big optimization. So we don't need to do more things and we don't need to do basically anything smart than that to further reduce the downtime. That's basically that's what we think. But obviously we can try if really needed in the future. And here's the results, the comparison. it's like hundreds of times faster than the natural disconnect mechanism, and also it's very reliable. And the most importantly, it's guest unaware. So and then just 1 or 2 pages to talk about some other maybe not that important stuff. First to think about is a forward and backward compatibility. It's easy to do that across versions. We can easily do that, but the only it's also a fancy stuff to think about. But just need to confirm. Just want to confirm this first. If we really want to develop these features, because when you actually upgrade Dbdk versions, it might be also you're likely upgrade other stuff too. So maybe it requires a code reboot of the maybe such as drivers and firmware even. And also we can think about if we want to use like other components to do the transfer, such as maybe the protobuf or anything else. But this is some design choice. Just be careful with if there's more components and more things involved, it's likely to sometimes get in trouble. And the key objective is, of course, reliability. And finally, just one open question: do we want to have it in Dbdk? There's no easy answer here. Just if you have it in Dbdk, basically it would be good we can have the synergy to improve this, and also people can use this out of box, and it will be supported cross versions. But then you will have more in the future, if to maintain this, it's going to cost more effort. And if I don't do that, it's opposite side, right? Okay.
Zhihong, we actually have a quick question just before. You want to run through the summary first? I know we're running short on time. I do have a question from from an attendee here.
Mm-hmm. Okay.
He asks, this is from Chen Bojia, and he asks, since this is for OVS Live upgrade, how is physical port handled properly during the upgrade?
Okay, physical port, right? For physical port, it's case by case stuff. If you, when I say case by case, it depends on the NICs, like what the vendor support. For example, you can use different VFs to make sure that the two processes can start in the same time, or you can maybe and when you use two VFs, basically you need to switch the traffic between the VFs, right? And then if you use other, maybe you can even duplicate that if the vendor support that. So that's for the physical NICs. Do I answer the question?
That's great. Thank you.
Okay, no problem. Right. Okay, here's a summary. Basically, it's just what we talked about, right? We want to solve want to make sure we can have guest unaware, and we can do some rapid iterative development to the virtual switch, and so this solution can be can like run like millions of times without failure, and also it can accept a lot of changes. It has no like other requirement to the basically the application. So okay, that's thanks. So any more questions? Sorry about the time that we wasted in the beginning.
Any more questions for Zhihong? Question here.
Okay, maybe you talked about it, but I didn't hear it. does it involve using a Dpdk multiprocess feature, actually, in order to maintain the state of the NIC, for instance? So is your solution assuming that you have multiple Dpdk processes sharing the same Dpdk state or not? Because if not, yeah?
No.
No. Okay,
Yeah.
so if the
No.
process goes down, the NIC should be turned off, because even if the process goes down, there's a PCI reset function and it just resets the device. So the question is, how do you avoid it?
Because your with let me look at this page. Basically, the old one and the new one just they are started in the meantime, then in the same time, and they both have the basic NIC the device open. And you can use VFs, or you can you know, if it's I mean that depends on the vendor NIC what the NIC you're using, but
okay, so you mean that those processes are at some point in time they both are active, right? Both processes are
right,
active.
yeah.
So
yeah.
if they connect to the same NIC, do they use the same DMA queues, or the new one is using different DMA queues?
I think I definitely use different DMA queues.
Okay, so you have to reprogram the NIC to direct the traffic from the old DMA queues to the new DMA queues.
Yeah.
And that's why it's case by case basic, because some of the NICs may not be able to do that. Okay. Got it. Thank you.
I think we're about at the limit as far as time. Ji-Hung, thank you so much for that talk. It was fantastic, and we really appreciate you contributing and putting this together. Thanks. We have a round of applause. Okay, I'm proud to present our first live speaker, Maxime Cocola. He's been on the tech board for quite some time, and he is now currently has been our tech board representative to the governing board. And he's here to talk about open Dpdk to containers networking with VDUs. I will turn it over to Maxime. Thanks.
Okay, thank you, Nathan. Okay, so the motivation between this work is to provide unified and software-defined data paths to both VM and containers, with the goal of having a smooth migration path for existing workloads, and also to at least have the same performance that we have with current alternatives. And the goal also is to reuse as much as possible existing libraries and drivers, so that we can have a working and stable solution quickly. First, what is VDUs? So VDUs stands for Vdpa device in user space. Basically, it's just a new kernel Vdpa driver, like we have, for example, for NVIDIA MLX5 Vdpa or Intel IFC Vdpa. But this time, it's not to drive a physical device. Actually, it provides a way for to implement Virtual devices in user space by having dedicated VDUs control path, but with keeping the generic Virtual data path. And doing so, we can existing workload can reuse drivers that are currently available, so Virtual drivers, both in kernel and user space. So today, VDUs only support Virtual block devices, but the goal of this work is to extend it to also support networking devices. Let's start first with an overview. So the main building blocks of this solution are the VDUs application and the VDUs kernel module. So the VDUs application will implement the device control, but most importantly, the device data plane. And it connects to the kernel VDPA driver, so which provides the application with some CharDev interfaces. The first one is a global interface for all VDUs devices. So it provides some I/O control so that we can create some VDUs devices, destroy them, and it's also we can also use these I/O controls to get and set API version for backward compatibility. And once we have created a new VDUs device with this I/O control, it provides a new CharDev interface, which takes the names of the device we created. And this interface also provides some I/O controls so that we can, so that the application use them to configure and to configure the device, like setting up the virtues, for example. It's also used to manage the IOTLB and so that we can map the buffer descriptors. And it also provides ways to inject IRQs when we don't use poll mode drivers on the workload side. This interface also provides read and write syscalls so that the kernel driver can query the application for its device state, and also to update the application with IOTLB updates like IOTLB, like when some pages are removed, for example, etc. So when we have created a device, we want to attach it to the VDPA framework via the VDPA bus. So as others VDPA drivers, it implements several operations, like Virtio device specific operations, for example, to perform the Virtio features negotiation, to query to set the number of VQ, or to query the application with the maximum number of virtues it supports. It provides also some operations so that to manage the interrupts and to drive the DMA operations. And to be able to attach this VDUs device to the VDPA bus, we use a dedicated Netlink API. And this API is implemented in the IP route 2 toolset. So when we are here, we have two possibilities to use this device. The first one is when we want to have the Virtio driver in user space. So basically, Virtio user PMD. So when we do that, we use the Vhost VDPA driver, and it provides an interface so that applications like QEMU and Dpdk Virtio user PMD that support Vhost user backend to drive this device. We can compare it to Vhost user, for example, meaning that the VDUs applications will map directly memory from the user space application running the workload. And the other alternative, so what is interesting with VDUs is that we can expose the VDUs device to the Virtio bus, sorry, by using the Virtio VDPA driver. So Virtio VDPA is a driver like Virtio PCI or Virtio MMIO, and doing so we can then plug on top depending on the device type, either Virtio Net or Virtio Block. And in the case of Virtio Block, we can then use this device with the generic I/O subsystem from the kernel. And for Virtio Net, we can use the kernel stack, networking stack. One difference with Vhost VDPA is we don't map directly the memory. So for example, for networking, we don't map directly the SKB. We need a bounce buffer for security reasons. Otherwise, the application could, since, for example, SKBs are not aligned on pages, we could leak some kernel information to the VDUs application, and we don't want that. So they introduced a bounce buffer mechanism where the descriptor buffers are copied into this buffer. So now that we have done this overview, let's see how it applies in networking. In the introduction, I mentioned that we want to leverage VDUs so that we can use OVS Dpdk, for example, or any user space vSwitch to manage both the primary and secondary Kubernetes interfaces. So in this example, we have two VDUs devices that are managed by OVS Dpdk. The first one is attached to the Vhost.io VDPA driver. And so we get a Vhost.io net device. And we can, thanks to that, we can use it as the if0 interface, the primary interface of the Kubernetes pod. And the other device, the second one, is attached to the Vhost VDPA device driver. So we get a Vhost VDPA device that we can use as secondary interface for that could be used by the Dpdk workloads with the Vhost.io user PMD. So the idea, as I mentioned earlier, is to reuse as much code as possible. And what we want to do is to extend the Vhost library of Dpdk to support VDUs. And so we would like to add it as a new control path, like Vhost user. And doing so, we can reuse most of the Dpdk Vhost code. Most importantly, the Vhost.io net data path, which should require no change at all. So that's data path that is used in production. So having it is highly optimized, and so being able to reuse it without any change is a good thing. We can also reuse the Vhost part, the IOTLB with really minor changes. And what is important also is that for now, we don't have to do any changes to the Vhost API. So regarding the status, so I worked on a proof of concept so that in order to be able to identify gaps and start to run some benchmarks. So this POC is not completed yet, so it's ongoing work. But I could test it. It's functional with both the kernel Vhost.io net driver and the Dpdk Vhost.io user PMD. So both paths that I explained earlier. It has some limitations because I have not implemented everything yet. For example, I have not implemented the PCI config space, so that limits some features like multi-queue or MTU, for example. And it also does not implement the control virtue. This one is a big thing because without the control virtue, we cannot do multi-queue. And I've started to test some setup. So as mentioned, testing with Vhost.io net, doing some iPerf. So that's kind of similar to what we would do with a primary interface. Setups setups for Dpdk workloads using test PMD with Vhost.io user PMD, connecting to the Vhost VDPA interface, like Kubernetes secondary interface. And also, I've done some tests using Vhost.io with attaching XDP loopback program that could be, for example, used for the exception path of the vSwitch when you want to inject some packets in the kernel stack. So regarding the next step, so that we are early in the POC, we have to address the gaps that I mentioned earlier. One gap that I did not mention in the previous slide is the device reconnection. So today, it's not possible to reconnect, and that's a no-go for production. But yeah, that does not prevent to do some testing. We want also to investigate whether the bounce buffer mechanism is a bottleneck, significant bottleneck for the primary interface. The idea is to compare its performance with alternative solutions like VFpair with OVS kernel. But we also want to check whether it's scale or not, since we have some memory copies that are done by the kernel, extra memory copies. We need to ensure that it is spread on several CPUs so that if you have dozens of containers, all the M copies are not done by the same CPU. We would like also to integrate this work, this POC, to integrate on top of it some TSO work that is being done in Open vSwitch. Doing that, we would be able to compare apples to apples with other existing solutions. Yeah, so run the benchmark, and also for now we have not integrated it yet into Kubernetes. Regarding Kubernetes, the good thing is that the SRIOV device plugin supports VDPA for physical VDPA devices, and so we could reuse it in theory to be able to do the provisioning part. And finally, we will need to upstream.
Maxime, we have a question here, again from Shinbo Zia. He asks, when using Virtual User as the front end, will there be any performance difference between VDUs as a back end and vhost user as a back end?
So I have done some benchmark with TestPMD on this one. What I have seen is I get a 5% decrease in performance, and this performance decrease explains because when doing a vhost user benchmark with VirtIO user, we don't use the IoT LB layer. And in the case of VDUs, we need to use it. So we have that extra layer that costs a little bit, and I think we should be able to improve it. So we will not reduce to 0, but we should be able to reduce to a few, 1 or 2%, I think, the performance.
Thank you.
And to conclude, so reusing the vhost library is great, but we should be able to have a full solution quickly. But we still have some significant development, especially the control virtue. We don't support it in vhost user in vhost library today. We would love to add it. But it could be also useful for vhost user. So that even if we don't do VDUs, it could be useful. So if people are interested in this feature, the goal of this talk was to also send a call for collaboration. So we have several things to do. If people, other companies are interested, we could certainly collaborate. So I would like to give some credit. So VDUs has been developed by ByteDance, so by Yonggi Xi. Jason Wang contributed the VDAP framework with a lot of other people, and also Adrian Moreno, who works in my team and who works on the VDPA support for SRIOV device plugin. So yeah, that's the end of the talk. I'm open to any question. Last slide I have put is some resources for people interested and want to dive a bit deeper. Yeah, so the slide, I didn't manage to upload the slide to skate.com yet, but I'm sure it will be fixed today.
Do we have any questions? You can also post questions in the virtual chat. Do we have any questions from participants in the audience here? Any questions for Maxime? Hey. Maxime, thank you so much for participating and for giving the talk. We have a round of applause for Maxime, please.
Thank you.
Awesome. Okay, we're going to do a 15-minute break, and then we will be back again in a few minutes. The next talk at 11:15 is booting DPD application quickly by device composition. We'll look forward to that. Thank you. Testing 1, 2, 3, 4. Testing. Okay, I'm pleased to present our next speakers who will be zoomed in virtually and also, again, on YouTube. Proud to present Yahui Cao and Jingjing Wu from Intel on booting Dpd application quickly by device composition. And again, please feel free during the talk to post any questions that you have in the virtual chat. If you're here physically in our audience, you can raise your hand and I will get you the mic. Take it away, guys.
Okay, so yeah, I will start introduce this topic. So it's great here to share our some exploration about this. So our topic today is booting Dbdk application quickly by device composition. So this is Yahui, and also Jingjing is still in the channel. So let's take a look at our agenda first. So firstly, we will introduce the background about why startup time matters. So especially in the cloud native ages. So and then I will give some analysis about how the Dbdk startup time is consisting of, and what is our benchmark results for this, and what is its problem. So, and then due to the problem, we find that we've proposed our proposal, which is the virtual device composition to solve this problem. So we'll give an overall idea and some detailed design about our proposal. And then we were given one of the methods to implement this virtual device conversation, which we call platform assisted BDC. And also you may also hear another name is our Intel Scalable LV. So, and then we will give some takeaway and conclusion. So let's go to the first topic. First page. So, so in the current world, so the whole industry is evolving from the monolithic application to loose coupled module. So normally, this service will be deployed as a microservice in the container runtime interface. So due to this architecture, so it has a very strong requirement for the service elastic deployment and first service online. So, and this is needed for application to boot quickly. So this is why startup time matters here. And also let's take a look at the trend happening in the AM3 industry. So in the very early stage, all the network function is deployed as a monolithic application directly on the host machine. And things depends on so much components such as host OS and other things, hardware. So, and it will not be so flexible. And then later we put all this network function inside the virtual machine, and then which we call this virtual network function or VNF. So because this application is packaged as the format of virtual machine, so it will be more flexible for it to be migrated to the other place and also good to be maintained. And then later, so the cloud native network function is introduced, which means we put all the service inside the cloud native environment. Typically is a container runtime environment, so that the container has lots of advantages, as you know, like finer grained sharing resource, lightweight, flexible, and kind of this. So if the data plane container network function choose the Dbdk as the underlying infrastructure, then the Dbdk based microservice start time matters a lot. So this is our background. So next, we will give an analysis about the Dbdk startup time. So firstly, we choose TestPMD as an example to do the analysis. So normally we list the components here to consist of our startup time. So first is the EAL initialization, which is the runtime init. And then after the runtime, so normally we will go to some memory allocation, like mbuffer, which is typically used for TXIXQ. So after the runtime environment and the memory has been set up correctly, so we will start the configure device, and then the rest of part we list them as other. So let's take a look at more detailed this startup sequence diagram. So whenever we start the main function, we are calling this RTEAL init, and then we go into this bus prop stage. So you can see here we intentionally list this bus prop because later you will find that bus prop performs lots of difference under different use cases. So in the bus prop stage, so we will scan all the device under this bus and then prop the device driver here. So and then next in the application, so whenever we create our mbuffer pool, we call this package mbuffer pool create to build a memory pool storing the mbuffer. So and after that, we just start the port, which means we are calling this RT either Dev API for the device configure and device start, all these things. So next, we will give our benchmark results. So firstly, we take the AFXDP as the comparison versus the single LV. So AFXDP, as you know, is kind of bypassing mechanism, which is quite popular in the cloud native ages. So we take this as comparison. So let's take this picture. As you can see, there are several parts here. So this orange part is bus prop, time consumed, and the green part is memory allocation consumed, and device configure is red part, and the rest of the part is the gray color. And as you can see that, so no matter for the AFXDP or the single LV, so they almost consume similar time for the memory allocation, device configure, and other part. But for the single LV, you can see it takes lots of time in the bus prop stage. So this is a startup time killer. And as you can see that, so the bus prop stage time it takes, it is larger than the overall time AFXDP booting takes. So as you can see, this is the problem on the single LV. And then we will give our proposal here. So this is we call virtual device composition here. So let's take a look at the some ideas. You can see AFXDP can boot very fast, but it has not so much high performance I/O. And for the single LV, actually, as the data show in the last slide, you can see this, it takes too much time on the booting stage, but as we all know, it is high performance. So can we find a way to combine these two things and take both of these things advantage and put them together? So this is our idea. Just we taking data pass-through, and also the control path emulation. So which means we can achieve both fast boot and also performant I/O. So as you can see in this picture, this dashed line means control path. So whenever our device PMD wants to access the device resource, it will always go into the virtual device composition module and then go into our hardware resource. And for the data path, it just bypass the host OS and directly go into the underlying hardware. So next, we'll give some more detailed design. So for the virtual device composition, actually we're, as you know, this is a virtual device. So we're composing a device from a collection of hardware source like queue, TXRS queue, interrupt, and kind of this. So this is the overall idea. So whenever we say we're composing device from the queue and the interrupt level, this means in the data path, we need to support the final grain sharing at the queue level, not at the device level. So this is the final grain sharing requirement. And also, since the data path performance I/O is mandatory, so we still need a direct DMA read-write from device and going directly into the user space. So DMA read-write is also mandatory. And once we use the DMA read-write, we need to make sure it does not attack the other user space, domain, or memory. This means we need to do the I/O address space isolation. So this is for the data path prerequisites. And for the control path, as you know, we're composing the device, which means this device, we need to intercept every access to the device resource so that we can let this, so that this module can behave like whatever it wants because we intercept every access. And then next we'll give some architecture diagram. So this is overall, there are two ways to, for the virtual device composition. There are two solutions. So as you can see, one is device specific, another is platform assisted. So no matter for each solution we choose, actually you can see the green part here, they're all the same. So which means, as you can see, let's firstly see the control path. So whenever user space process or user space driver I want to access your device resource, it will always fall into the virtual device composition module. And then in this module, it will do some configure and finally grant you some resource it wants or not. So this is for the control path. As you can see, the control path is always being intercepted. And for the data path, as you can see, it always bypassing the host OS, VMM, and directly going to the underlying hardware. So, and when we go into the hardware, you will find that. So since this is the DMA read-write, so we need to do the I/O address space isolation. So, and as you can see, the difference here is that the isolation method is different. So for the device specific part, which means, so if your device support device specific fabric has this ability to do the I/O address domain, to do translation and isolation, which means your device can translate all these things by yourself, and then whenever queue is issuing your DMA request, it will go first, like going to the device fabric internally, and then go into your space. So you can implement your own specific method. So this is one solution. And another solution is that, so if your device does not support this, then you can leverage the platform's capability. So you can see the platform has provided a DMA mapping functionality, which means can help the device to do the DMA domain translation and isolation. But there are some prerequisites for the device, because the requirement is that the physical device needs to support this passive capability. So the passive capability is PCIe specification defined capability, which means whenever your device wants to send a DMA request, which is packaged as a PCIe TLP. So your device can add a passive prefix at the start of the PCIe TLP. And then when this PCIe transaction is going from the device into the root complex, the platform IOMMU can capture this passive prefix so that the platform node can, by combining the passive and the bus device function from the PCIe transaction, it can uniquely mark our device by this BDF plus passive, so that by this unique ID, the platform can identify the correct domain, which is corresponding for this device, so that the platform can help you to do the DMA translation and isolation. So that is the whole idea. So let's take a simple look back. So if your device supports the IO address space translation, so your device can implement device-specific way. And if your device does not has not this capability, you can leverage the platform's capability. And the only requirement is that you need to add this passive capability support. So, and this is our solution. And then we will take an example as one method for this virtual device conversation, which we call platform-assisted virtual device conversation. And also, this is actually the Intel Scalable V. So Intel Scalable V is a newly developed Intel virtualization solution targeted for the next generation CPU server platforms like Sapphire Rapids. So as you can see, I list two paths here to help you understand. So for the data path, it still has the pass-through, which means all the data path is bypassing the host OS directly going to the user space. But at this time with the passive isolation, which is look quite similar as the last slide shows. So this means also you need to support final grain sharing. And in this, we just put all the queue interrupt as a resource set, which is calling assignable device interface, ADI here. So, and also since we are directly issuing DMA with write, so we had our native performance, and also we had our hardware enforced isolation, which is also already shown at the last slide. So, and for the control path, as you can see, whenever a PMD trying to access a device resource, so all the access is intercepted by the virtual device conversation module here, so that it is very flexible for the virtual device conversation module to manage the device life cycle. So, and also since the interception is, we have intercepted all the access to device resource. So it is also friendly to do the device snapshot and also like for the LAN migration case. So next, let's see how our implemented way to improve this overall startup sequence. So let's firstly take a look at how the single VVF consumes so much time. So since all the time is being consumed, it is falling into the bus prop stage. So we have a more detailed analysis for the bus prop stage. So you can see whenever we probe a bus, and you can see we were doing some falling into some PCIe bus level, it needs to reset so whenever from your space falling into the kernel space in this VFI module, then we need to perform the PCI function level reset because this is a real PCI device. So we need to follow this device cycle. So as you can see, this device this is consume lots of time here. And also when we doing the driver prop stage, as you can see, or when the driver wants to do some register or MMIO access here, so all the register access has been bypassed to hardware, which means we need to follow the hardware designed life cycle or timing here. So, and then for the ScaleLV case here, as you can see, we also listed the similar sequence diagram. And the difference here is that, so whenever we're doing the bus level init reset, and when we fall into the VFRO here, so it will issue the device reset request to the driver or hardware. And then in this case, our virtual device conversation module will intercept this reset request. And then, since this is a virtual device conversation by software, it means we no longer need to follow this PCI device timing here, because we're not a real hardware device. And also, though there's still some hardware init reset happening internally in the hardware, but this virtual device conversation allows software optimization so that we can greatly improve this time consumed. And also at the driver prop stage, so as you can see, whenever the driver wants to do the device resource access here, so also our virtual device conversation module can intercept all these access so as we can do the optimization as well. So, and next we will list our benchmark results after using this method. So before this, we will list some dependency here, because it's a solution across the quite some components here. So for the Dbdk part, we need some changes here. So firstly, we need to add a new NIC PMD driver here, so that we can prop this and init this device. It's actually it's a virtual device here. And also we need to introduce our new bus model, which means we by this bus model, we know how to scan, discover this device, and do some initialization if necessary. And for the host part, we need to add a virtual device conversation module so that we can intercept every access from the PMD to the underlying hardware. So that this gives us so much benefit we've listed before. So, and for the device part, as you can see, there are two solutions here. So if your device supports IO address-based translation or isolation by yourself, yes, that is fine. And your device can do the DMA translation by yourself. And if your device does not support, does not implement this logic, so you can leverage our platform, which has the passive aware IOMMU. So in this way, your device needs to support PCIe passive capability. So whenever your device wants to issue a DMA request from some queue, so you can add a passive prefix at the start of the TLP. And then when the PCIe TLP is going to the root complex at the platform, the IOMMU can capture this passive. And by combining the passive with the bus device function, it can help you to do the domain translation and isolation, so that with these overall components, we can implement the overall solution. So next is our benchmark results. So firstly, let's look at this rest of the part. So as you can see, we take AFXDP, ScaleLV, SingleLV together for the comparison. And for the memory allocation, device configuration, and other parts, actually they consume almost the same time here. And for the single LV, as you can see, it consumes lots of time, but compared to the single LV, ScaleLV has decreased this startup time by lots of, and as you can see, it is a 4.6 times boost, which is a very promising improvement and boost. So, but still, as you can see, comparing to AFXDP, since it is a kind of software device, so it does not have, it consumes almost 0 time at the bus prop stage. So comparing to AFXDP, so the ScapeLV can will still consume a little bit more time than it. So overall, as you can see, so the application running on the ScapeLVs, so it actually boosts a little bit slower than the AFXDP, but it's for the application running on the ScapeLV can boost 1 times faster than a single LVVF, if you see this. So it's quite a promising improvement here. So next is acknowledgement. So yeah, sincerely thanks for the great help from Steve Lian for brainstorming the overall idea about this work and reviewing the slides.
Yeah, we do have a question here from an attendee. What about using a Virtuo VDPA?
So actually, we do not have some, do not compare the VDPA here. So I think maybe we can have some more data after we benchmark this. Yeah.
Fair enough. Thank you.
Yeah.
We have some questions here from in-person attendees.
Okay, so I will proceed. So yeah, this is the last page. So there's some key takeaway. So firstly, we introduce our the background. The startup time matters especially in the cloud native ages, and also for the device pass-through. As you can see from the data benchmarked, it has challenge on fast boot, but still it has a good performance. So and then we propose our new design, which is called device composition. So and then we propose the overall design idea, and later we show one of the virtual device composition method, ScapeLV, and show this its performance, and it can effectively boost startup time along with high performance as device pass-through. So and we had a white paper link here in our website, which has more detailed data and information here. So if you have any interesting topic, related topic to discussion, please contact me and Jeannie. Yeah, thank you.
Yeah, we have a couple of quick questions. We're getting close to the wire here, but if you don't mind, we have a couple of quick questions from attendees here in the audience. Can I pass it off here?
Thanks for the talk. Can you maybe give us an idea of how much time it is in like seconds or milliseconds? Because you're only talking about like 5 times speed up and that it's very long, but how long is it in fact?
Yeah, I think it's milliseconds level actually. So we can save about 100 milliseconds levels a time.
One other question. Is this somehow related to mediated devices that came up a couple of years ago? I believe they also came up from Intel, right?
So yeah, this is a good question. So the media device is actually deprecated. So we are not we are following the community's latest progress, which, as you know, is IMMFD. So actually, our total solution is based on the latest IMMFD solution to do here.
Yeah, we thank you.
This is not based on MDev. Yeah.
Thank you so much for taking the time to contribute to user space and giving your talk and answering questions. We really appreciate it and we enjoyed it. We have a round of applause, please.
Okay, thank you.
Thank you. So I'm here to, I'm ready to introduce the next speaker here. We have GK Fan Zhang from Intel, and they'll be talking about a refined, comprehensive Dpdk crypto dev asymmetric crypto dev framework. Thank you.
Welcome, everyone. My name is Kai Ji. I am a software engineer working for Intel Ireland. Most of my work in the past few years were focused on crypto dev development and Intel crypto acceleration hardware QAT enablement in Dbdk. Today, I would like to draw your attention to what we have done on the asymmetric crypto framework in the past few months. Before we started, I would like to thank especially to Eric Christoph and Shimek Zegan. They have significantly contributed to this project. This talk won't be here without their support. Now, without further ado, let's begin. For this meeting's agenda, we want to talk about currently status on the Dpdk asymmetric crypto dev in 2022, some highlights we did in common asymmetric crypto dev, API changes, data structure rework, etc. And then we would like to get a discussion about the currently issue in the asymmetric testing and some unit test refactor we have been working on. And what's the future works we're planning for the asymmetric crypto dev in Dbdk. Unfortunately, most of the topic covered in this talk are based on the code walkthrough, so I do want to apologize in advance for no fancy diagram here for my slides. Okay, now, what have emerged in Dbdk 22.07 release? We have about 30 patches have been accepted related to asymmetrical crypto development since beginning of 2022. Among those 30 patches, 17 of them are asymmetric crypto dev changes on common data structures and APIs. At this moment, we also have about 13 patches related to asymmetric crypto in the patchwork backlogs. Most of them are in V1 or V2 state. Now let's go to some highlights changes in 2022. So first is asymmetric crypto key exchange operation type. Originally, the key exchange type enum are defined in the asymmetric op type enum, alongside with op encryption, op decryption, op sign, and op verify. Actually, the use case of this key exchange operation, like private key exchange, private key generation, public key generation, are unrelated to those asymmetric operations. Therefore, we separate the asymmetric key exchange type from the op type enum to make it clear and more readable. In the PMD compatibility op type bitmask, both op type enum and the key E type enum are supported and not conflicted. For example, in RSA, the op type can be set to sign, verify, encrypt, decrypt. In DH, the op type can be set to KE type, for example, like private key generation, public key generation, or shared secret compute. The second changes, based on the previous changes, we move out the DH key exchange operation type from X-form structure to DH op parameter structure. The DH key op now are dereferenced from the RTE crypto op instead of asymmetric session pointer. The reason behind this is a single X-form session should be well enough to perform both DH operations. For example, in the shared secret compute, a pair public key need to be generated. So you will be assigned this to public key generation plus shared key compute. If KE type still in the X-form members, a session will have to be created twice for this same group of operations. It also help to DH to extend to support elliptic curves as well. We also add a new elliptic curve Diffie-Hellman parameter structure, which called the crypto ECDH op params. Inside of these parameters, we include the KE type, which I just described before, private key, public key, and share secret. Private key is unsigned big integer in big Indian format. It is output pointer as public key if the KE type is private key generate. Its input private key, where its KE type is one of public key generate or shared secret compute. In case of a private key length is 0 and the KE type is set to public key generates, a random generator compatibility device will need generating a public key. We'll need to generating private key to use it for public key generations. A public key pointer basically is type of crypto EC point structure. It's made by RTE crypto params. X and Y represent as X coordinate and Y coordinate used for the elliptic curves. It's output pointer to a public key where a KE type is public key generates, and it will be input for pairs public keys when KE type is share secret computes. Like a public key, the share secret basically is output point to calculate the share secret when KE type is share secret computes. We have added a new padding flag in asymmetrical op structure. Diffie-Hellman padding is used in certain protocols. By default, the public key and share secret will be padded into the left with 0 to the size of defined hash algorithm. Even same protocol might be used in different approach. For example, in TLS 1.2 or 1.3, they have different padding configurations. If this flag is set, the public key will be returned without a leading 0 byte. And if this flag is not set, a public key will be padded to the left with 0 to the size of underlying algorithm. And this is the same behaviors for the share secret as well. We also clarify the usage of RSA paddings. As more padding configuration members added into a padding, therefore having a separate structure for padding parameters will make more sense. However, this padding structure is still located inside of RSA op param structures. Supported RSA padding hash algorithm are MD5, SHA-1, SHA-2, SHA-384, SHA-512. There's a number of padding styles. In PKCS15, is only used for RSA signing operation. This field is used to determining value of the digest info structure. Therefore, specifying which padding algorithm is used to creating a message digest. For encryption or decryption, this field is ignored. And OAEP and PSS inside of this padding will need to be specified which hash algorithm is used for padding scheme. We added MGF1 hash is for mask generations for PSS padding and OAEP padding. Also, the soft length and the OAEP labels is common parameters to PSS and OAEP paddings for RSA. One thing is worth to mention when RSA padding none and the asymmetrical op verify is selected, the cipher pointer in RSA op parameter structure should be output to be stored for signature decryption without padding. This has never been, it's been worth to mention there. Okay, so what was the problems in asymmetrical crypto unit test app? What we're facing? So currently there are 5 unit test suite supported in Dbdk test, OpenSSL, QET, CN10K, etc. So by nature of the asymmetrical, it's very complex. We have covered a lot of different scenarios. Test scenarios need to cover a different variation of operation time, such as encrypt, decrypt, sign, verify. private key generating, public key generating, shared secret computes, not to mention in different modeling size, key size, padding configuration, etc., etc. So we also need to have some flexible configuration parameters, so we can configure those options easily. It's good to have some reference results so that we could compare the PMD result with the correct result so that we know PMD is functioning correctly. And then we should have less maintain effort. All of those are currently missing. So we are introduce automate unit test framework refactor. So with all the problems in mind, we create ATS rule structure to capture the asymmetric parameters that need to be executed. The rule contains a configuration of the key size, op mode, padding configurations, modeling size based on the test algorithm. And also we are using random number generator for input plane data generations for another required data if needed. Also, once we have a rule created, input data generated, and we are using OpenSSL to perform same op and to generating accept result and stored into input data result pointer. A typical op function call flow can be once the test op function calling compatibility check to the PMD to see compatibility supported, then we prepare asymmetric transform session, create a session calling incube burst, dq burst, then we can compare the result in the end. So this slide is showing an example of RSA unit test structures. Inside of RSA vector structures, we have X-form type that just E values. This is just a snapshot. The actual content, it will be much more bigger. It will contain sign values, D, P, Q value for all the asymmetric usage for RSA. And on the right-hand side, we have RSA rule configurations. Inside of the rules, we will have, in this case, we will have key size 1024, RSA key types will be exponential, padding configurations none, plain data length 128, and this operation will be RSA encrypt and decrypt. Once everything has been set up and we feed into OpenSSL engine, we're taking leverage of the OpenSSL PMD, and you see exactly same function call but built into this automation test. We're calling RSA public encrypt or RSA private decrypt or private encrypt to perform whatever the rule has been configured. One of test example result will be looks like this. So it will be have similar styles of the current Dbdk unit test. It will be dump out all the generation data has been generated by random generators and execute all the rules test. So on the right, you can see it will be this test will be generating RSA key into exponential keys or quadruple format. And once all passed, it will be generating a nice result to showing exactly the same what happening here. Okay, that's pretty much what I want to address for this talk. For next step, we have EC point verify function need to be merged for crypto dev. For QET, Intel QET accelerator engine, we have ECDH currently ongoing. We want to materialize the ECDH. For the asymmetric unit test refactor, we are currently supporting RSA. We are planning to get a DH or DSA integrated before for this 22.07 release. The previous OpenSSL are implemented based on 1.1x library, so we also want to support for 3.0 library in the future. And we're also seeking for opportunity to do a crypto API sample code showcase. for this asymmetric unit test refactor. Of course, this work cannot be done alone, so I would like to thank you for Kira Power, Brian Donnelly for code reviews, John McMara for project management, Fiona or Maxim for QET support. Okay, that's all from here. Thank you very much. Any questions?
Do we have any questions from our in-house audience at all? Any questions for Zhikai? Okay. Any questions at all? No? Okay. Xi, thank you so much for taking the time to talk to us today and presenting your work. Really appreciate your input, and it's great to hear about what you're doing. So thank you. We have a round of applause for Xi.
Thank you for having me. Have a good day.
It's a pleasure. So we're going to take a short break, and then we'll be back at 1:15 with Akil Goyal, who is zooming in to talk about RTE security. Thank you so much. Here, our next talk is from, zoomed in virtually, this is from Akil Goyal, Marvell Semiconductors. And the topic is RTE security, support for inline MACsec. Let's give a big welcome to Akil.
Hello everyone, and the topic for discussion is RTE security, support for inline MACsec. So here's the agenda for today. I'll briefly touch upon, recap on the RTE security, and then we'll do the MACsec overview. And what we have proposed is the Dpdk MACsec control path APIs. We've introduced 2 new APIs for SC and SA creates. I'll talk about SC and SA in upcoming slides. And we've introduced a new XForm for MACsec in RTE security session. And then I'll talk about this MACsec and RTE flow, how we can configure MACsec flow into to work on to encrypt or decrypt the packet inline during inline processing on the NIC. And then we'll talk about the MACsec data path, and then some device capabilities and stats, and we have some patches. We can have a look at that. So RTE security is a library, security lab, provides a framework for management and provisioning of security protocol operations offloaded to hardware-based devices. These devices can be a NIC or a crypto PMD, and basically the NIC will be a smart NIC, and it can operate. It can do crypto operations while doing the packet processing from the Ethernet. So it provides a generic APIs for create and free the security sessions to protocol full protocol offload or the crypto operation on the NIC or the crypto device. Basically, this framework is currently supporting IPsec, PDCP, and DOCSIS protocols. As of now, we are introducing the new protocol called MACsec. So MACsec is defined by IEEE as 802.1ae standard, and it allows authorized systems that attach to a LAN. It maintains confidentiality of transmitted data at layer 2, similar to what IPsec does for layer 3. It takes measures for the packets which are transmitted or modified by unauthorized devices or users. It will basically drop them, and it also facilitates secure communication between organizations using the same LAN. It will be useful for people who are using same LAN and basically in some co-working spaces which can have multiple customers which are mutually suspicious to each other, and it can provide secure communication on that end. It can isolate DOS attacks also. Now the packet layout for MACsec is like Ethernet frame. When it comes, the source address, MAC address, and source and destination MAC addresses, ether type, and payload. When this is encrypted using MACsec, new ether type is added, and it is defined as 88E5, and a security tag is added, and the payload may be encrypted or it may be plain as well, depending on the configuration. And it will add an ICB for sure. This ICB may be 8 or 16 bytes, and the sec tag will be optionally 8 bytes or 16 bytes. The sec tag fields are basically these, and these are like PCI, AN, short length, packet number, and SCI input. This is this SCI secure channel identifier is optional, and it may or may not be used. It depends on the PCI field, the SC. If this bit is set, then SCI is valid. Otherwise, SCI is not there. The other fields in PCI is this V is version number. It is explicitly set to 0. And ES is the end station bit. And this shows that the SCI is not valid. It is for end station. This SCB is single code copy broadcast, which is for EPON cases, and E is for encrypted payload, and C means that the payload has been changed, basically due to encryption, and AN is a 2-bit field with values 0 to 3 to identify which assay is used for encrypting this packet. I'll talk about this later as well. So this is a diagram from 802.1ae standard to specify the MACsec operations. The user data, when it is up for MACsec protection, it will take basically the AN field. It identifies which SA key to use, and it will also use the SCI and packet number to define the sec tag, and based on the parameters, it will do a it will generate a secure data. It may be encrypted or just authenticated, and if it is, it will also generate ICV for specifying the authenticated data. When this packet is received at the other end, it will again choose the SA key based on the SCI and the AN values, and it will check the packet number, and it can also do anti-replay checks based on the values which are already set for the window size. And once the packet is validated and the sec tag is valid, and it will show up, it will give the user data, plain user data, and the packet is received back to the application. MACsec has some architecture objects like the SecY entry or the security entity. There's an instance of the MACsec implementation within a particular node. It participates in only one connectivity association. Connectivity association is a group of secure nodes talking to each other. It may have multiple secure channels. The secure channel is a unidirectional channel from one node to many, and it may be associated to more than one SAs. So SAs is a key keys which will be used for encrypting the payload or the packet. So this is the base. This diagram shows the one-to-many configuration of various entities. Like many flows can have a same SecY entity, and many SecY entities can have same SC. And SCs can have multiple SAs. Basically, we have AN values from 0 to 3. So that's why we can have 4 SAs with which can be associated to a particular SC. We had in the previous slide, I talked about a SCI field and a AN field. AN field determines which SA to use, and SCI field will determine the secure channel, which secure channel to use. So these all cannot be in case of RT security. We only have one API to create a session. So these all SecY entry or the SC and SA, these all cannot be accommodated in that. So we introduced 2 new APIs, which I'll talk about in the upcoming slides. So this is the control path for Dpdk that we have introduced. First, we will introduce a new API for creating a new SA. This will give you the SA identifier, which will be used to create a SC. This SA ID will be, these SAs will be like multiple SAs will be created, and for each of the AN values, SCs can be added in that. So once the SC is created, SC identifier will be returned, and it will be used for creating the session. This session is a RT security session, and we have introduced a new MACsec XFORM to specify all the options that we have for session configuration. So the output of that session would be RT security session pointer, which will be set as the action field in RT flow creation when the security pattern is formed. When the pattern is matched, then the action will be like security, and the action.conf will be set as security session. So these are the MaxSec APIs that we have introduced. First is SA create, SA destroy for creation of SAs. For SCs, we have SC create and SC destroy, and the RT security session create and session destroy, what we do for IPsec and PDC2. It will be just changed with the MaxSec X form in RT security session cons. So here are the parameters for SA configuration, like the direction of the MaxSec, whether it is TX or RX. The keys, the key will be basically only for AES GCN, as the MaxSec specification only specifies AES GCN as the algorithm for MaxSec processing. It can be of 128 or 256 block size, and the length of the key will depend on that. It also has a 96-bit value of salt, which will be used for encrypting the payload. And next is the AN value, which I just talked about. And this SSCI, it is a short secure channel identifier. It will be used for extended packet number cases, similar to what we have like extended sequence number in case of IPsec. This XPN is the extended packet number, the upper 32 bits of the 64-bit packet number, and this last one, XPN, is the lower 32 bit of the packet number, which is expected to be coming up for the encryption of this of a packet corresponding to this SA. This value may be 0. It depends on the implementation whether it needs that or not. And if it needs that, then this is the first starting packet number that that will be expected. And beyond that, before this packet number, all the packets will be dropped. Now there are some SC parameters. Again, there will be like the S direction is there to specify the RX or TX direction. It will be it will help us in getting the SCRX or the SCTX. For RX side, it will be having a set of 4 SAIDs, which will be created by the RT security MaxSec SA create, and these will be set here. Next is the SA in use. Like it will be used to specify which SA is currently in use, and we can specify like only one SA is currently used, or all 4 SAs can be used. This SC is active or not, this 1-bit identifier is in that. And for TX side, we can also have a facility for rekeying of the SA, and if the key has expired, then we can have a SAID for rekeying also. We can specify it at the initially when we create the SC. It also has a 64-bit value of SCI, which will be used if send SCI is set. Send SCI is part of the MaxSec X form, which will be in the next slide. So this is the MaxSec X form. Again, the direction and the algorithm. This algorithm can be like AES GCM with 128-bit or 256-bit, or it can be for with XPN 128 or XPN 256. XPN means extended packet numbers. This cipher offset is the start of the encryption, from where the encryption needs to be started for the MaxSec. This SCI field, it is to be used for RX flow identification or to set SCI in packet for TX when send SCI is set. This SCID is created by the RT security MaxSec SC create in the previous slide that we talked. Now it has some RxSecY and TXSecY properties which can be set. What can be what we want replay window size, or we want to validate the frames. It can have multiple options like which are stated in this hash defines. Whether to drop the packet once the packet is not correct, it will drop the packet, or it will just give an error. It's just given warning and not drop the packet. It will pass through that packet. It will specify that in this validate frame. Next is the ICV include DASA. So it includes, it means that the ICV that is generated, it includes the source MAC address and the destination MAC address on it. Next is the control port enable. Next is preserve sectag or best preserve ICV. This will, when the packet is received, after decryption, what will happen to the sectag and ICV, whether we want that to be removed in the application, or we want that the PEMD or the hardware has removed it. So if we set these bits, the sectag and ICV will be preserved and application can use that. Replay protect is the flag to enable replay protection, anti-replay protection. For a TXSecY, we set the MTU and the sectag offset. Sectag offset depends on the sectag insert mode. It specifies whether it is at the offset is at a fixed offset from the start of the frame, or it is at some relatives offset. It will be used for matching some VLAN tags. Now this protect frames is to enable MACsec protection. It will do encryption and authentication or not. Next is the ICV includes DSA, which I explained in RX side also. And now these all bits will be used to generate the sectag, like the sectag version, which will be 0 always, and end station ES bit. This will be used for ES bit. This is for SC bit. This is SCB bit, and encrypt. This bit will be used to, if this bit is set, then in the PCI we set both the C and E bits. Now next is the once the security session is created, we associate that with the flow, and we can create a MACsec flow, and a new flow item has been created to identify the MACsec flows which the user can use, and then user can use a combination of Ethernet, VLAN, or a MACsec flow item as pattern to create new flow rules, and use flow action as RT flow action type security, along with action.conf is set as RT security session that is created for MACsec. Now the flows, this flow is similar to what we did for IPsec, except that the flow can be created for inbound as well as outbound in our MACsec case. But in IPsec, we only set it for one case. That is inbound. For MACsec data path, there is no special handling required for MACsec. For inline NIC, user can use directly its RX burst or TX burst and do RX TX of the packet. No special handling is required for MACsec flows. If there is some error in transmission or reception of the packet, then it will be notified as an error event, which I'll talk about in next slide. For look-aside case, it will be same as that we were using for IPsec. Like I talked in the previous slide, RT flow rule will be created for both RX as well TX. So we do not need to set the packet metadata, which is required for IPsec. Now these are the error notifications that the PMD or the hardware can specify, like when the packet is received, then what is the error in that particular case. So it will do a validation of the sec tag, whether it has some bits in the sec tag which are not valid, or it will specify using this event subtype. And similarly, it will also notify whether the hard expiry or the soft expiry of the packet number has come or not for receive and transmit. Now there are some these all MACsec functionality cannot be supported by all the PMDs. So we have some capabilities. So the PMD can specify the various capabilities that it can support, and based on that, application can decide whether to do that processing or not. Now, for MACsec statistics, we have introduced 2 new APIs for SA and SC statistics, and this takes SCID and SAID as inputs to get the MACsec SA stats or the MACsec SC stats. The sec-wise stats will be we can get it from the RT security session stats get. It is a generic API for all the RT security protocols for similar which we do for IPsec or PDCP or DOCSIS. Now these are the patches we have for the mailing list, and V1 was posted I think 3 weeks back, and so you all can review those patches. The Ethernet implementation will be submitted in next few weeks, and will be giving the implementation for Marvel CNXK platforms to support inline MACsec protocol offload. And a test application in Dpdk test will be introducing new option to validate this feature. So that's it. Any questions now? Thank you.
Thank you, Akhil. Any questions at all from our in-house attendees or virtual? If you have any questions, you can also put them in the virtual chat for Akhil. We got a question down here.
I've got just a short question. So does it blend with Mac in Mac encapsulation?
Sorry.
Does it Does it cooperate? Could it be used for Ethernet frames that use Mac in Mac encapsulation? When Ethernet frame encapsulates other Ethernet frames, because this is like one of the telecom use cases.
Yeah. Yes, it can be used. There is a field for cipher offset, which can be used for giving you the offset from where we need the encryption. So it can do such combinations, and similar. You're talking about Mac in Mac, right? So there can be options for VLAN also. We can incorporate those as well. We can use this cipher offset and the sec tag insert mode. Combination of these can help us in identify where to encrypt and where to start encryption.
Thank you very much. Any other questions for Akhil? Okay. Well, Akhil, we appreciate you taking the time to zoom in and chat with us and talk about MACsec. And yeah, let's give a round of applause for Akhil. There you go.
Thank you.
Great talk. Oh, we'll be taking a break here for lunch shortly, and we will resume at 1:55 with the next talk. And we look forward to seeing you back then. Thank you very much.
Okay.
Testing.
turn around. Because I need maybe pointing the stuff, right? For example, like this way. Oh, test. Testing. Okay? Testing. It should be fine, like this way, right? Okay. Okay.
Test. No, just for.
Hey there, welcome back. So for our next speaker has been a key member of our tech board and a key contributor thereof, Bruce Richardson. I know he was sorry he couldn't be here physically, but he's happy to be here virtually, and we're glad to stream him in that way. I've had the experience of working with Bruce quite a bit on our tech writer hire, and a great guy and a great contributor to the community. He's here to talk about Dpdk Dma Dev interface, the design and use of copy offload APIs. Happy to welcome Bruce. Thank you.
I'll have missed, so I just have to make do with the virtual presentation this year. So as was introduced, I'm going to talk a bit about Dma Dev in Dbdk. So before I dive into the detail of the talk around the whole design of the data plane APIs and their use, I'll start off with a bit of introduction to Dma Dev itself for those who are not familiar with it or who haven't looked into it in any great detail. So first question then is naturally, what is a DMA device? Do not all hardware devices that we deal with in Dbdk do DMA? Do NICs and crypto devices? Well, the answer is yes. Obviously enough they do, as we all know. But whenever we're talking about DMA devices in the context of Dma Dev, we're primarily thinking of accelerators for copy operations and other similar operations. So our Dma Dev supports devices which do things like memory to memory copy or memory to device copy, and similarly device to memory copy. They also often will do things like fill operations, and these accelerators often can do various other types of operations that are not currently part of our API, but who knows, they might be in future. I know certainly our Intel accelerators can do things like comparisons, they can do some form of checksumming, things like that. However, for the purposes of this talk, I'll mainly refer to them as copy accelerators, and we can think of them primarily as a mem copy accelerator, because in the context of packet processing and the work done on Dma Dev, it's mostly been around copy, but not exclusively so. But it's just easier if we think of them as mem copy accelerators for now. Okay, so how did this support come about, or when did this support for these copy accelerators, these Dma Devs, come about? So before the 2111 release, so basically our LTS release from last year, before that, we did have support for Dma devices in Dpdk already. We had this support via the Rsa Dev APIs, and for those not familiar with it, Rsa Dev is kind of a catch-all bucket for devices that really don't fit into any other category, and it provides some fairly minimal set of APIs. So anything on top of that, specific for your device or device type, has to be done via private APIs. So for Rsa Devs, we had pre-2111, we had DPA2 QDMA, the Intel IOAT driver, and the Arcachon TX2 DMA driver. So these were 3 devices that all did similar functionality. But the problem was, being under Rsa Dev, they all had device-specific APIs. And then anytime somebody wants to add a new one, and in fact, a lot of the stimulus or impetus for developing Dma Dev was the arrival of potentially more Dma device drivers, was adding these new device drivers involved duplicating code from the existing ones, copying and pasting it, which we saw, or else inventing whole new APIs, which makes problem 1 worse. And we saw both of these situations arriving. So that led us to try and come up with a common abstraction for these copy accelerator Dma Dev type devices. So this effort was the work of quite a number of people. It was a multi-vendor, multi-user collaborative effort in the community. It was a great example of that collaboration. Special call out to Cheng Wen, who did who steered the original Dma Dev patch set through to merge. But even if you look within that patch set, just at the core Dma Dev API header file, you'll find that there's multiple license companies called out who have contributed to generating this multi-vendor, multi-user infrastructure that is in use. Okay. So then, what does Dma Dev support or provide? Okay, well, like many of our, or in fact, all of our existing device abstractions, we have things like device discovery, you know, where you can iterate through devices, get the count of the number of devices you have. It also then naturally provides capability reporting. It provides channel and device configuration. Naturally, then they're all the control plane side of things. Then once that's all set up, you have your data plane operations. So the Dma Dev supports the operation offload and the completion retrieval at the end, and finally device shutdown. Now, in this talk, I really don't want to go into too much detail into that control plane setup configuration side of things. It's not actually that complicated. The diagram shown on the right here is taken from our documentation. The documentation does have some more information about what these various abstractions are. But at a high level, for an end user, really, you end up with a single hardware DMA channel, which is really the independent piece of hardware that you would use. These are each backed by a single Dma Dev instance. So one hardware channel corresponds to one Dma Dev. Whether or not those hardware DMA channels all belong to a single DMA controller or multiple ones doesn't really matter, because they're all independent of one another. So you've got just independent devices from a software point of view. Each one corresponds to Dma Dev. On top of that, then you have got these virtual channels which provide a certain amount of context if you're going to be doing different types of copies. Sometimes you may have hardware, like for example, our Intel accelerators, you only need one DMA channel on top of it, and you send all operations down to it. In other cases, you may need to have different channels if you're doing different types of operation. But in the simple case, if you look at our example application for DMA, you generally, if you're only doing copies, memory to memory copies, you generally just need one device with one channel on top of it and send the operations down to that. So that's the very quick overview of Dma Dev. Just finally to point out that there are already multiple drivers available, which is not surprising because, as I said, there were multiple hardware vendors already involved in this standardization effort, and there were already drivers available there that just needed to be taken from Rsa Dev to Dma Dev. So After that, very quick whistle-stop tour through the history of Dma Dev, such as it is, and the very high overview. I'd like to spend the majority of the rest of the time on this talk just looking at the actual fast path and the APIs that are involved there, what format they have, and why certain decisions were taken in the design of that. Hoping that this will be useful for other people. Well, A, for users as to how to use them, and also then potentially for other future API design as well, and what the trade-offs that were being made whenever we were involved in this collaboration. So whenever we were designing the offload APIs, there were a number of constraints that had to be taken into account. First of all was we couldn't use mbuffs. I mean, ETH uses mbuffs. Mbuffs are ubiquitous throughout Dpdk. When writing a Dpdk application, you really can't get away from using them. But on the other hand, when looking at a copy offload type API, the API had to work with non-packet data first off. Okay, we couldn't assume that everybody just wanted to be copying packets around the place. It could have been control plane information. It could have been data from a lookup table. Who knows? Also, we couldn't assume that it was always whole packets that need to be worked with. So an mbuff for a packet contains the pointer to the start of the packet and details about the length of the packet, but you may only wanted to have copied some data, let's say 256 bytes into the packet and 512 bytes of a 2K packet thereafter. So it had to work with data in the middle of the packet. So you couldn't actually use the packet mbuff header. We also needed, so because of this constraint about not using mbuffs, mbuffs could theoretically have been used as the header for passing this information around, but it would be kind of wasteful because it's a 128-byte data structure. So really, we needed another method to pass around this, source buffer, destination buffer, length of copy information to the APIs. And then secondly, that was for sending the data down to the accelerator. For pulling the information back from the accelerator, we needed another method to return context on completions back to the user, so the app could continue where it left off before it did the offload. As always with Dbdk, our second constraint was performance. We needed a very low offload cost. This is perhaps more relevant for Dma Dev and copy offload than for some other workloads. The reason being that CPUs can already perform copies pretty quickly. So if you want to get good value for your DMA acceleration, you really need a low offload cost, because if it takes you, let's say, 50 cycles to offload a copy operation to a piece of hardware, the CPU can probably do quite a large amount of data copies inside a 50 cycle budget. So if that's the case, then there's no point in offloading that copy operation. So the smaller the offload cost, or the lower the offload cost, I should say, the smaller copies that can be offloaded to get value from your accelerator. So that was an additional constraint, though performance and low offload cost is always something we have to keep in mind, obviously enough, in Dpdk across all device types. So then, going a step further down into these specific APIs. The APIs really kind of fall into two categories for the data plane. One, there's job submission, and then there's completion retrieval. So the logical step is job submission first. So that's kind of what I'll talk to first. Okay. There were two real options that could be chosen between for the design of the offload API. Okay. The first one is shown in kind of pseudocode kind of diagram here on this slide. It's to follow the standard model in Dpdk of using batch operations and to do a batch offload. Okay. In that case, the code inside the application driver would be something along these lines. Starting from the top left, we would have inside our application a loop going through the packets. Now, I know I said we don't always need to copy packet data, but for the purposes of these illustration and for simplicity, we'll assume it's the packet data we want to copy here. It's probably the common case, okay? So we'd have a loop going through each packet. And for each packet that we want to copy, we would have to create a job structure indicating, where the copy was to start, where the copy was to be copied to, how long it was to be, and any other additional flags that needed to go alongside the copy operation. And that flags may actually include a set of flags that says this is a copy operation rather than a fill operation. Okay. After that loop, then the application would then call a bulk NQ API. So like RT-DMA NQ, for example, would be the API giving the parameters as shown there, basically the list of jobs being passed down to a device. That in turn would go through our Dma Dev layer into the driver itself. That's kind of the part in black in the diagram, where there would be another loop in the driver, which would iterate through the list of the job structures that were passed in and take each job parameter and create a hardware descriptor for it, which would be written to the descriptor ring of the device or whatever equivalent there was, and to be followed by a doorbell at the end of the burst. Okay, so that would be the general flow that there would be in a normal batch offload situation. Okay, so what are the advantages and disadvantages of this scheme whenever we compare it to the second scheme, which I'll outline in a second? Okay, so the advantages of this kind of scheme are it's very similar to other APIs in Dbdk, particularly EastDev1, which is the one most people are familiar with because just about everybody who uses Dbdk has to use NIC or X and TX burst at some point. The other advantage is that we only have one driver function call or one indirect function call via function pointer per burst of packets. Okay. The disadvantages, though, is that it's requiring the application to have a little bit of extra memory to build up the array of structures. But more importantly, though, it's requiring the CPU to spend cycles building up this array of structures. Particularly, it requires a set of extra stores and then loads again before the final set of stores. So you're essentially having to store twice all the data about the copy, once in the temporary structure and then a second time in the descriptor when it gets to the driver, with the load of that data back in again in between. And loads and stores can often be a bottleneck inside applications. We can be quite I/O bound on the cores. So this is a potential problem. Secondly, or related to that, it means that all data past the driver is done via memory, or the vast majority of the data being passed into the driver function across the function call is done via memory. We're not taking advantage of the fact that on most architectures and with modern ABIs, you can actually pass data via registers. That's not actually being done in this case. So that led on to the second style of API that we could come up with. And I'm sure most of you are aware this is the one that was ultimately standardized in the Dma Dev API. But in this case, we would have a single operation being offloaded at a time with a separate doorbell. So what this looks like, again, using the same style of diagram, is we have our loop in the application. And also in the application, we have a submit API at the very end. So the actual application is still has the same rough idea. You loop through each packet, but instead of building up a data structure here that is then put into an array and passed to function, we go directly into the driver. We call Dma Dev copy, which goes to the driver, which creates a hardware descriptor immediately. So the only stores are those that are absolutely necessary. Okay, we go directly to the descriptor. And then at the end of the loop, we can call our submit API. Though, as a side note, I'll also point in that as part of the API, one of the flags you can pass in for an individual copy is to have it submitted in directly. If that's what you want, you don't necessarily have to call the submit API. But anyway, that's tangential to the specifics here. So we loop through, call copy per individual entry, and then do a submit call at the end. And that submit call basically just has to write the doorbell, no other additional work, no loops inside the driver code itself for that offload. So the advantages and disadvantages here are largely the inverse of what we had for option one. So the advantages are it avoids having the temporary array of structures in the application, which means that we avoid having to write out two sets of structures for each operation. And we can also take advantage of the fact that in modern ABIs, the data being passed into a function can be passed in via registers. Note here, how many and what types of parameters does depend a bit on the ABI. On x86-64, it's 6 registers. I know ARM allows you to pass in a bunch of parameters via registers, and I assume PPC and other architectures similarly work in the same way. So this can make your function calls quite efficient, not having to store data to the stack or in structures to pass in. So it makes your function calls quite cheap. The disadvantages then are the inverse of the other advantages. We have got extra indirect function calls or function calls via function pointer. There's now one for each operation rather than one for the burst. And we have got a slightly different style of working to other APIs, even other offload APIs like potentially CryptoDev and others that work on bursts. So they're the advantages and disadvantages. However, at the end of the day, the option 2 was indeed chosen, and the main driver for this was performance, because there had been, as I mentioned earlier, a number of previous raw devs for DMA acceleration, and the prototyping that was done whenever these were developed tended to show performance benefit. We certainly saw it in our testing for the IOAT driver, and there were others in the community who proposed similar style drivers of raw dev who had, for the same reasons, that they saw that it gave slightly better performance when they were doing their testing. Another side effect or advantage of this that I quite like was that the APIs were simpler and more readable, since the operation type was actually encoded in the name. So you didn't need to specify a generic operation with an enum for the op type as the first parameter. Instead, you could actually explicitly call a DMA copy, DMA fill, so you can see clearly in your code you're doing a copy or fill operation. It's a minor thing. Some people may not like it, but I for one certainly do. So that's the offload APIs and why they were chosen, that style in particular was chosen. I can pause briefly at this point. I think I'm okay for time if anybody has any quick questions on this. Otherwise, I'll take the rest of the questions at the end.
Any questions for Bruce from the in-person attendees? Any questions at all?
If not, I'm okay to go on, and I'll take them at the end.
I think you're good to go on.
Good to go on. Good stuff. So it's stunned silence, perhaps, on that end. Hopefully, though, not everybody's asleep with the, I'm not sure how good a lunch he had. Anyway, on we go. The second part of the data plane APIs are the completion management ones. So what happens after the copy has been done or the fill operation has been done? What style of API is there? So this has a different type of problem behind it, okay? So these completion APIs are all about how do we manage the context for the app to resume processing where it left off, okay? So it's just requested that a copy operation has been done. You want a buffer copy from A to B. Presumably you're going to do some work on either A or B or both once that copy is complete. So how do you know where to, when it's done and what the pointers A and B were, for example? Okay, so it's all about retrieving context, and that's what the completion APIs needed to do. Again, the considerations involved. First of all, the pointers A and B that you actually sent down to the hardware and were written to the descriptor are generally not the context you're interested in. If we think of our mbuffs, our mbuff data pointer that we write to our NIC to receive a packet is not the pointer we get back from the Rx burst function. We get back instead the mbuff pointer, the pointer to the metadata, rather than the pointer to the data itself, because that's the context we need to work with. And it's the exact same case here. The pointers sent down to the hardware are not necessarily what we need to come back up. Also, as I already explained, we don't have the mbuff data structure there. So we don't, and we also don't have an equivalent structure that we want to return, okay? For Dma Dev, because we're doing copy operations mostly, it's different to a number of other offloads because we are guaranteed in the copy case to have at least 2 contexts per copy. We're going to have something to do with the source and something to do with the destination. Okay, or in almost all cases. There may be cases where you only care about one of them, but for most cases, I think it's fair enough to assume that we'll want to have some information about the source and destination stored. This context can also be in variable size depending on the application. And this is something I certainly saw when I was looking at the IOAT driver in the raw dev, and then thinking again about it for Dma Dev, and looking at the work that was being done on a Vhost library. Your context can vary from time to time. I originally thought, well, we probably need 2 pointers of context, one for the source, one for the destination. Will that work for us? That's a lot to store in the driver. Can we get away with 1 pointer? And then thinking of the Vhost case, in some cases there, our context might actually be a pointer for one of the buffers and maybe a ring index for the other. So storing 2 64-bit pointer values would be a waste of memory. Other applications may have even more context that needs to be stored. So this can be a variable size depending on the application. And the other consideration then is tracking all this in the driver, particularly if we want it to be variable sized or the size of the context to be runtime configurable. It's liable to slow the driver down, perhaps unnecessarily. And the driver cannot know what the best format to store this context in is. So it may do it in a suboptimal manner. So we sidestepped all these problems by changing slightly the normal approach again of dealing with context. Instead of returning pointers on completion, we just work entirely off indexes. And we therefore allow each application to track its own context in the most efficient manner for that application. So how this works is, as you send the jobs down to the Dma Dev accelerator, you get back, after you call Dma copy, you get back a job ID. So first time you get back a 0, then the next one you get back a 1, 2, 3. So it's an incrementing by 1 each job you enqueue. Then on completion, the accelerator, the Dma Dev APIs actually will return to you some information that you can use to retrieve your context based off that ID. It will tell you the number of jobs completed, and it guarantees that they will be, completions will be order is a separate issue, but they will be reported in order. And also you'll be given the job of the last completed ID. Okay, so in the case of you offload 5 operations and they're all completed, you will get, when you call RTDMA completed, you'll get back the number 5, and then 4 will be the last ID. So at that point, you know that job 0, 1, 2, 3, and 4 are all completed. So between these two, that then allows the application to do its own tracking in the most efficient way that it can. The app can store the context. Generally, you expect it to store it in a ring, but the question is, you know, is it more efficient to store a single ring containing a structure with multiple fields, or is it more efficient and for the application to perhaps use multiple rings? So if we think of the Vhost case or something similar to it, where we may want a pointer and an index, you probably want 2 rings in that case. One, a ring of pointers, which are all 8-byte entries, and a separate ring of, let's say, 1-byte indexes, so that you're not wasting 7 bytes per ring entry. So it does give you the flexibility in the application. Or an application which wants to track a relatively large amount of context, perhaps 20, 30 bytes per copy operation, is free to define a structure and put it in a ring there too. The final point that I'd make on this is that the actual IDs are not, the numbers returned are not actually tied to the actual configured queue size inside the device. So the IDs always go up to UN16 max, so basically 64K, which means the application is free to scale its ring for tracking context to any size it wants. Well, up to 64K, obviously. If you configure the hardware to have a ring size of 1K, you can still configure your app to use a 2K context ring or 4K context ring, or potentially a 512 entry 1 if that's what you want as well. It's basically giving full control to the application and also ensuring the minimal possible overhead for this tracking in the driver, which is basically just has to track some numbers, some numeric IDs. So it's very lightweight on the driver. So the last point, or the last thing I'll discuss in this talk, because I see I'm getting on in time, is that for those who have looked at the API, you'll notice that there are actually 2 separate completion functions. Now, they both work off IDs, but there is a small difference between them, which is probably evident from the name. One is called RTDMA complete. I'll just touch briefly, particularly for end users who are looking at this API, as to why that is and when you might want to use one or the other. So if we look at Dpdk specifically, most software using Dbdk should probably or will probably be offloading jobs with Dbdk pin memory. And so those jobs should never fail due to memory errors or bad pointers. So for this case, your basic API, or the first API, RTDMA completed, is probably perfect for this use case. It can flag errors, but it doesn't flag any details. Basically, you've got a pointer parameter at the end called hasError, which can be, if you pass in a pointer there, it'll set it to true if any error is encountered when returning these results. Basically, if some of the operations failed. If you're writing an application and you're confident that you're always using pin memory and you're always giving valid pointers, you can even set that to null and just assume everything always works, and that's fine. However, there may be cases where you need a bit more detail, or there may be errors that could be returned. For example, Intel DSA, which is the hardware behind that uses the IDXT driver, it'll support non-Dpdk memory as well using SVA, shared virtual addressing, which is, I think, the term the Linux kernel uses. SVM is the equivalent term in the PCI spec. So this is where the memory control doesn't have to be programmed by Dpdk IOMMU. Instead, the kernel driver is taking care of the mappings for us. Depending on how that's configured, there may be cases where the memory you're referencing is paged out at the time you offload the operation, and you need to handle that case. So we need kind of an error reporting that says, hang on, you just need to touch this memory in software to page it in, and then retry the operation or do the copy in software. So that's one possible error condition that could theoretically happen in some cases if you're not using pinned memory. There's also the possibility of future expansion into other areas. Like I said, a number of hardware accelerators will support memory comparison. If you're doing a memory comparison, you kind of need to know whether the comparison was successful or failed, or whether it matched or didn't match, I should say, rather than success or failure, because success or failure can actually be separate from that. You could do a comparison expecting the comparison not to match, in which case it's successful. So there's some fuzziness there. So I think match and non-match is a better term to use there. But in any case, we need to return a value to let you know the result of that comparison operation if we add that in future. So that is a possible future use case as well. So because of all these, we also have the completed status API, which gives you fine-grained status reporting. It'll return an actual array of status values, one for each operation that completed. So again, if you have 5 jobs, you get an array back of 5 values, not just saying they completed, but it'll actually say job 1 completed successfully, job 2 failed, job 3 was successful, and so on. So it can handle multiple errors in a burst rather than just saying an error occurred somewhere and leaving it up to you to sort it out. Okay. So my time is pretty much up. So this is a summary slide. I've talked about Dma Dev being the new API. I've talked about the data plane APIs for NQ and how they're single rather than burst oriented. I've talked about how the completion handling works, both in terms of using IDs and also the possibility of returning error values to the user. And at that point, I think I've got 2 minutes if there are any questions before my time slot is up.
Just as we're wrapping up, do we have any questions from in-person attendees or questions online? If you want to post them in the chat for Bruce. Hey.
You mentioned that you took, or that there are many optimizations in the API and the implementation you chose. Do you think that such optimizations could also be beneficial for like the crypto offloading and other offloaders?
Potentially, yes. It will really depend on the use case, but it may well be worth trying. It'll depend on the complexity of the APIs, number of parameters, and things like that. The nice thing about the DMA or the copy offload was we had a fairly small number of constrained parameters. So if you think of how you were offloading a basic copy operation, you had, I think it was, we were able to keep it to 6 parameters to that API because that was all the information we needed. They all fitted in registers. It became a very simple offload API. For the context tracking, that's perhaps more applicable in other places too. But for existing APIs that are already written a certain way, it may be quite a big change. But this is why I'm giving this talk now, to talk about our experience and what the trade-offs were so that, you know, maybe others maintaining other subsystems may be able to get something from it, or it may be the case that they say, yeah, that's nice, but it's not going to work for us, which is fair enough.
Bruce, I think we have one additional question here.
Are you able to get a completion for a batch of requests, or it's always one request, one completion?
It is one request, one completion.
But wouldn't it speed up things if you could batch?
Would it speed up things if you could batch? It would, and in fact, depending on how the driver implement things, it could be well working off batches under the hood. The one thing I will say is the specification for returning the status says that the user should initialize or pass in an already zeroed array. So in the case that everything is successful, not written to. Okay, so it's only in the error case that we actually will go and fill in the individual status values as to why it failed. At least that's the way it works right now. So in the all successful case, you're not going to get any benefit because we're not doing any writes anyway. And I know certainly the IDXT driver works exactly in that way. We get a batch completion, and if that's all okay, we just move on and ignore it. It's only in the case that it says there were some failures that we go and do further checks. Would this be of use to end applications? It might be. It's something certainly we could think about, and I'm happy enough to have a direct discussion on this if there are use cases where we think it might be useful beyond what we have now.
Thank you.
Thanks so much, Bruce. Thanks for taking the time to speak with us and share your contributions.
Just
one other question.
Another brief question. Did you think about, well, defining the API around the corner cases like that the size you want to copy is 0 or things like that that always are problematic when thinking about malloc or memcopy, not malloc?
Special cases for particular copy sizes? No, we didn't. How would you think that would work since we're writing down to an accelerator? Would this be, you have a special RT DMA copy 64 byte? Is that what you're thinking of?
in the end, if I have to make sure that the values I copy there or the ranges I copy there meet some requirements, then I have to pre-check all these requirements in the user code. At best, for some common use cases like you just want to copy an arbitrary number of bytes, which could also be 0 bytes, I do not want to check it in the user code because I think the API should still work with that.
Certainly for the 0 case, we probably could make that work. The question is, do other users or do all users want that checking to be present in the API? So there are a set of trade-offs because the more smarts you put into the API, the more overhead you're adding into applications that actually don't need that smarts. So if you've already got an application that is never going to offload a 0 byte because it's already caught that earlier in the pipeline, it probably doesn't want to have to pay the cost of doing a check on the data passed into the copy offload operator to check for 0 bytes there, where it knows it's never going to happen. So there's trade-offs to be made there on that, but it is certainly doable. But I'm not saying that necessarily everybody's going to want that.
Okay, thanks.
I think we're down to the wire on time. Bruce, thank you so much for taking the time to talk with us and share your insights. Could we all give a round of applause for Bruce? Really appreciate everything you bring to the community.
Thank you all. Thanks for listening, and thanks for the questions.
Be well. I'd like to introduce our next in-person speaker here. I hear Liang Ma is here from TikTok, and he is here to talk about Dpdk memory allocation optimization. I'll turn it over to him.
Hi, everyone. I'm Liang Ma. Came from TikTok UK system technology engineering team. Today, I'm very glad to share some interesting funding with Dbdk memory allocation. Okay, so I changed the title a little bit. I changed the title to revisit memory allocation in Dbdk. The reason for that is I remember this topic was discussed in previously Dbdk summit around 2019. The reason we need to revisit this is I believe, because our fantastic tool, unit test tool, that Dbdk malloc performance test, that tool is not available back to a time. So I believe the measurement might not be that precisely. And also today we will come with a different perspective for this. And also we have some new funding with this as well. Obviously we will also propose a different solution as well. So basically today's agenda. First, I will do a short summary about our user case and our challenge. And the next, we will discuss a little bit about existing solution. And after that, we will discuss about the proposed solution and our POC, and also our POC's performance result, and how actually the benchmark environment and the setup, right? And then that's a summary. So for the challenge of our memory allocation, during my research, I just realized the memory allocation actually is an extremely complicated topic, and that's very, very sensitive with the application user case and the memory access pattern. Sometimes that's not really an apple-to-apple comparison. So it's really hard to draw some generic conclusion about that. So today, all my discussion here is based on our user case, basically, our team user case, basically. So in the following 4 challenges, first one is very easy to understand. That's the latency, right? So in the traditionally, latency is extremely sensitive with data plan, right? Data plan, because we have more and more bandwidth, 100 gig, 200 gig, 400 gig even. But recently, because our control plan's scale also increased rapidly, we found, even in the control plan, the latency does matter, okay? And the second part actually is overhead. Overhead, for the more academic term, I should use internal fragment and external fragment, all those things. But that's maybe overcomplicated, for today's talk. So I just put all them all together. Just overhead basically means in order to allocate all this amount of memory, what's the price? What's the actual memory you need to use to to do that? That's definitely sensitive, right, for the cost. Because in any kind of service, the memory just means money. If you can save memory, you're basically saving money, right? The next one will be the scalability. Scalability is all the time is very, very important. In my opinion, there is 3 perspectives for that. First thing is, when you increase the processor number, the performance will degrade linearly, right? And also, when you increase the overall system memory capacity, the behavior will expect consistent. And the third one, also, you need to be flexible with different request signs, right? For example, for small signs, the behavior should not be that different compared with a big request sign. That's my understanding for this. The last one is really about our user case specific need requirement to how to deal with really large number of small objects. So how I define large here and how I define small here. Okay, long for short, large here basically means more than 1 million. The small object basically means something smaller than 256 bytes, generally speaking. Okay. So traditionally, Dbdk memory allocation patterns, right? There's 2 different categories. One is for control plane, another one is for data plane. For control plane, we have the RT-malloc and the RT-zmalloc, etc. API to deal with that. Most of them is used during the initialization, right? When you create RT-rin, you create all those hash table and you create memory pool, etc. You will use all those kind of that's setup API, not just this 2 I mentioned here. Also include that memory zone reserve, etc. The speed and performance is relatively slow compared with the fast path, right? So in the data path, traditionally we use the RT memory pool, right? This one, mainly usage for this is for PMD. So PMD will do that mbuff allocation and free, etc. And that's fixed the signs total, and that's really fast. I will describe that details a little bit later. But the recent years, interesting enough, more and more data plane application, like the user space protocol stack, starting use RT-malloc. So occasionally, from the mailing list, I saw some community members complain with that RT-malloc performance about that user space protocol stack usage. Okay. So this is today's RT-malloc overall architecture. Okay, that's my personal understanding. The first layer here, that's the system memory segment. Okay, you have a bunch of them. All this is organized with a list. And built on that, you have the heap list. That's another list. Each heap actually will cover one socket. So my understanding is each socket you will have one heap here. So this heap basically have two parts. One part is to link all the allocated elements all together. Another part actually is 13 buckets. This 13 buckets is depend on the size, right? As a free list. That means as a free element available for allocated from. So this is a very, very typical and classical body system setup here. Okay. For example, in the bucket 0, this one just covers 0 to 256 bytes, right? You have the free element here, and then you move on. You have the 256 bytes to 1K as a bucket 1, and etc. until to the end, the 12th buckets that cover 1 gig to 4 gig. So overall, that's a very classical body system, and each of this kind of free element can be split to smaller one, move to another bucket list, and also when you free that, these two smaller element can be merged and relocated to a bigger size bucket as well. It's very, very typical classical body system here. Something really interesting here is when the pre-allocated memory is run out, what's going to happen? What's going to happen is once the pre-allocated memory run out, then the system actually will go back to this memory segment to searching help. Give me more memory segment here. This part of logic is related to some the memory segment list sorting processing here. And then the allocator will get a new memory segment put in this heap, and then all this list will have more free element to use for allocation. Okay, that's very important. I will use this logic in the next part. Okay, before we jump into any RT limitation here, I must highlight one thing. RT-malloc itself working perfectly, okay? Working perfectly and serves its purpose perfectly, no problem. This limitation just for our user case, because in our user case, this limitation actually have impact to our application. So I just put this kind of challenge contents here, okay? The first thing is, I just introduced a little bit about our benchmark setup. So this benchmark actually is based on our brand new unit test. That's the malloc performance test. So we just keep request 10,000 1 meg block memory from the Dbdk memory management system. And we also set up the overall memory capacity to that application with the socket limit option. That's the EAL options. You can control the upper limit of your memory assigned to this unit test. So we try with setting 4 gig, 8 gig, 10 gig, 16 gig separately, okay? That means not all your 10,000 allocation requests will be successful. Once the test will stop when the system run out of memory, have no memory to use, then stop. And then we got this latency numbers. Okay, you can easily find the latency actually not really consistent even for request the same size memory, 1 mega memory. So the latency actually increase logarithmically like this way, right? Very interesting one. I believe this is because, okay, personally I believe this is because that memory segment list processing issues. When you run, because we do that 10,000 times memory allocation, it's easily run out your pre-allocated memory. So this end up with, you need to go back to here to searching help, right? To reprocessing with the whole list. You have more memory, basically means this list actually is longer. So your processing time may be longer as well. So I believe that's why majority reason for, we see this latency increase, okay, here. And the second part for this is a heap scope lock. So if you dig into the HTML code, it's very easy to figure out where the spin lock cover quite big scope. Basically, that scope is cover each heap. Each heap is basically means each socket, right? So it's quite big scope, So this lock is not that bad, seriously for the control plane because you won't have 100 control plane cores running right in the same time. Unlikely, right? Maybe 1 or 2. But this one potentially can damage your user space protocol stack performance, potentially, because the user space protocol stack actually is data plane, so can run on many cores, potentially, can impact that. The second challenge actually is from the overhead for the small object. So this is another test. This test actually, we just dump all the the overall element size the Dbdk memory management system use under the actual size we request. So this is a result. So for one example, when we request like 77 bytes, right, with the request size, you can notice the overall element size is extraordinarily large, right? The reason for that is, again, because Dbdk use a very, very classical, linked list to management all the allocated element. So this require you put a 2 cache line metadata just besides your pointer address. So that means each time when you try to freeze that pointer, it's very easily just do arithmetic, pointer arithmetic to figure out where is the metadata. It's very easy, very nice. But it came with a price. The price is for small object, you see, the overhead just looks a little bit large. In our case, if we're going to create 1 million, this kind of small object, our memory overhead became unacceptable in our case, okay? By the way, I need to highlight this test setup again. So this test actually is a setup based on Intel Xeon 8275 processor running with 3.0 gigahertz. And also, it's very, very typical Dbdk setup. We isolate all the cores with a standard way. And also, we set up the huge page size is 1 gig. Okay, so this is a setup. And we only run this test with 1 core, 1 logic core. Okay, the hyper-threading is enabled, so I need to highlight this in advance, okay. And we talk a lot about RTE malloc, and then we can look into the RTE memory pool. RTE memory pool actually is a really nice design. It's fantastic for data plane. It came with some special assumption is the overall the pool size is total size that's fixed, and also for each unit inside of this pool the size also fixed as well. This one also included the local pool. Local pool basically means here, so each logical core has its own local cache. So that means each time when it's request or free, you are not necessary to go to request the global resource at all. You needn't touch the global resource try to avoid that, even cast operation contention at all, right? And just use the local cache. And here, just a very, very standard RT RAM-based memory pool. I need to highlight this is RT memory pool just as a framework, API framework interface standard. Underneath, there's 8 or 7 different implementation here. This is RT-based. We also have another maybe 4 and 5 software solution. Also have a couple hardware vendor solution for the memory pool as well. This one is fantastic, but this one have a very, important assumption, like this fixed total size and fixed unit size. This is not really true in our use case. So this is not our solution at all. So here I would like to introduce our POC and our proposed solutions objective. So first one is I already mentioned, highlight this, right? So the RT-malloc serves his purpose very well. The code quality, everything just good. We have no intention to touch that part of the code at all. That code running for years and robust. We don't want to touch that code at all. So we propose our solution as a Dbdk library. Because we are going to deliver the presentation in Bordeaux, so I just named that API as a BD malloc and BD free. I think maybe that's an interesting one, okay? And after that, all the allocation compare with the traditional memory allocators. We are just working on the Linux system heap. This one need allocate all the stuff on the huge page, okay. Also, maybe we support like a pre-allocation with kind of design rational. In the design principle, we will do the pre-allocation. We will have the local cache. We support flexible size here as well. And we hope, ideally, we should have lower latency and a smaller overhead. But this tool, okay, this tool just keep in mind, the lower latency and the smaller overhead heavily depend on your use case, how you use it. Okay. So I hope this is working for our use case by our design. Maybe can turn to more generic if community put more input here. The last one is really friendly to large number small object, right? If this tool actually we can successfully achieve this two objective, I think we can achieve the final one as well. Instead of jumping into tons of details, so our POC and the proposed solution is not that complicated, but still have quite lots of details there. So instead of jump to the tons of details, I rather than use this 1,000 feet view for this POC, for this solution. Our first rationale behind this is we try to do partition. Partition means you have the control structures here, and the cache and all this segment, memory segment here, is per core. Okay, so each logical core you have all those. You don't need to compute it with any other logical cores. Okay. But also we will separate the control metadata and the place actually store the data. We will separate that one. That's a little bit different to compare with what the RT-malloc did. Okay. And also, we will try to use bitmap. It's very common in kernel, Linux kernel, or other modern memory allocator to use a bitmap to tracking the element starters instead of use that linked list. It's really is to save memory for small object. So the whole idea is, so first thing is we request a fixed size memory segment from the Dbdk heap here. So basically, we will use RT-malloc. We request fixed size. The fixed size we use here that's configurable can be 4 meg, can be 8 meg, depends. So each time you will, that's how we did the pre-allocation, right? So you will request 4 fixed size memory segment from Dbdk. And also, the funny thing here is because this one consistently just request one same size from Dbdk. So you always came to Dbdk, ask same size. Not really for this time is 4 meg, next time 8 meg, next time will be 4 KB. That's not the case. So each time you came to Dbdk, say, give me this size. Okay, so this one can make the Dbdk side, the body system, a little bit easier. And once you grab that memory segment, with the memory segment we get from the Dbdk heap, and then we will split that to a substructure. That substructure can we can name that like page. Okay, that's a very general idea. Name that like page. The page size can be 4K to 16K. It's also configurable. The 16K will more favor the bigger, bigger object, and the 4K page will more favor the small object. Will give you less internal fragment. Based on this pre-allotted memory segment, we will start build up our different science lab. Okay, then we can go to another way to introduce our category in this control structure. Inside of this control structures, we will differential the different size memory requests with two kinds. One kind is normal size, another one is huge. For the huge size, what we define here, normally it's configurable, but normally we define as anything beyond 32 KB. We thought that is huge. The huge one will go to use RT-malloc directly to, instead of, not really make that many sense to use our, poke. Anything under 32K here can be split to lots of different categories. That's a very traditional way you can do that with, powers of 2 or something in the middle as well. You have different, the bin buckets to hold that. So for each science, you can have this kind of slab. The slab can be 4K slab, 32 slab, 16K slab, etc. You have lots of this. So each of this kind of slab is aligned with the pitch size as well. For each 4K slab, that will split to lots of same size unit. So basically means you have a lot of 4K inside. If that's a 256 slab, then you have lots of 256 bytes unit inside. So each time, when you try to allocate anything, you're just searching the most suitable slab, and for example, if you try to malloc 253, very likely give you something from the 256 slab unit. And also, we put all the metadata actually inside. For example, for the memory segment, we put the metadata in the header in the top here. We're tracking all the page status and the space map. And also, we will put the base map into the slab headers to tracking all the unit inside in the status as well. The last one, also extremely important things, is about the cache here. The cache also have exactly the same, the size bin buckets as the slab. But the different things is each time all this cache will be pre-allocated, and then when the request came in, actually the request will first jump into the cache to search if this size stuff exists or not. Okay, sorry, I should introduce what's inside the cache. The cache actually just the array of the pointer. Just an array of the pointer pointing to the corresponding slab. So you pre-allocate all those slab units to the cache, and then next time when the application jump into here to request something for that size, you can just searching if the cache have it. If the cache already have it, you just give it to the application immediately, right? With really low latency. And also for the free, it's same. When the application starts free that object, you can check if that cache is not full. If that cache wasn't full, you can just put that pointer into this cache, and the free is done. Okay, it's really fast. And then we start do some benchmark for this. So all these benchmark have the exactly same setup, compared with my first, benchmark. So for which benchmark, the setup is we do the 10,000 malloc. Sorry, we do the malloc 10,000 times, right? And because we never free, in the middle. So that's the worst case for the whole system. Because keep request resource, you never free anything. That's the worst case for the system. And then with a very standard unit test behavior as a memory set to also turns on times. I believe this operation is to make sure you actually allocated something, right? Otherwise, if any allocation actually is wrong, this kind of memory set can cause corruption, okay? And then you do another turns on times free, and by this case, I must say the cache local cache not really take effect because it's so easily just run out cache. You cache just we just set most of them just 128 interest, so it cannot really support turns on the request, right? So it easily just run out and then turns into that slab system, and then also the slab system cannot support that because you have too many requests. Then you need allocate more slab. If the underneath memory segment is run out, you actually need to turn back to the Dbdk heap to request more memory segment. That's basically a chain. So the result is very, very interesting. So this is actually a latency comparison. You can notice when the request size is very small, our POC have some advantage, have much smaller latency. Personally, I believe that's the slab system pre-allocation is working there because you don't need to go back to the Dbdk that frequently. You don't need to go back to Dbdk heap very frequently because most of the time you can just working with your pre-allocated memory segment. But when the request size became large and larger, you will see their performance trending to the same. I believe the reason for that is we start came to Dbdk heap more and more frequently than before. So you end up with just have a similar performance with Dbdk RT malloc. So personally, I say this is worst case because in real life, unless you have turns on times request but never free anything, right? Too greedy. So after that, I also tested with some another extreme condition is the best case. The best case basically means you just do malloc and then free, and then just repeat turns on times. Okay, so in this case, your local cache actually working because you malloc free, 1, 1 interleaved, right? Malloc and free interleaved. That's very sweet for the cache, right? So you can see the result. The result, our latency is significantly smaller than RT malloc, and also that's not really increased when the request size increase that much. Also, the RT malloc, you see, I also tested with this blue one. You see the blue one. The RT malloc with malloc and then free interleave the pattern. This result also is better than the BD malloc worst case result. So that means it's across the slide. So this value actually is better than here this value as well. So the summary here, the takeaway here from this POC, an interesting work. I just got a following summary. The first part is the local cache is really a critical feature for memory allocator. So we just have less lock, we have less new resource allocated, right? So pre-allocation is crucial for small object, even not use the local cache. Because you don't need to come back to the Dbdk heap that frequently. So the memory overhead and the latency can be amortized with smart design, like we use bitmap actually, try to reduce the overhead here. So for next step, because this testing still is too ideal condition, you have the worst or the either worst or best, that's not real, right? So we need more testing on the real world workload. So in the real workload, it should be your malloc X times, and then your free Y times. Your X, Y can be very different depending on your application, memory access patterns, right? So we need to collect more real data from real world workload. And also we need to enhance our overall solution because this is a very early stage POC. We still have lots of work to do to refine that design as well. So final one is after everything settled down, we plan to upstream this to the community because I believe other community members will have similar situation with us, and we actually need something in the middle of the RT-malloc and the memory pool. This can be very helpful for everyone. The final one is thanks. So many thanks to Yu Bai and Dr. He Peng and Zhi Hong and Fan Zheng and Yu Wei because they gave me a lot of suggestions during my research work, and also many thanks to Anatoly and Dimitri for their fantastic work for the malloc preferred test. It's really, really helpful. It's just is there. This one actually is brand new, just upstream this year. I think this year March. It's very, very important for me to do this work. Okay, thanks a lot. Yeah. I think that's all for me. Okay. Any questions? Thanks.
Do we have any questions for Liang? We do.
Yes, thanks for this great presentation. Just a question regarding the algorithm. So memory allocation is not really something new, and there's the, I would say, famous tcmalloc algorithm that is used by tcmalloc from Google. And why did you decide to implement your own algorithm instead of just porting that to C?
Okay. That's a very good question. That actually is a question many people, my colleagues ask me. The tcmalloc, pkt-malloc, and the ge-malloc, all those malloc actually is there for years. The reason we need that, I think, I need to put back to here, yeah. So the reason we need that, first thing is all those things not a part of Dbdk, right? So that's just a third-party library. The second part for that is all those allocator is not based on huge page. All those allocator actually use the Dbdk, sorry, you use the Linux system heap as well. And also those allocator has their, they are tending to more generic. Their scheduling, their unit design is for thread, not really for core. Because in Dbdk, that CPU usage, we occupy the one core, with one thread, 100%. That's our use, our CPU usage pattern. But if all those generic, memory allocator not really designed for that. They're designed for very generic thread, right? And also, all those things have lots of fancy and advanced feature we not really needed. For example, some allocators support that tiny, like 2 bytes or 4 bytes, stuff. It's not really happened for us so far anyway. We don't need any 2 bytes or 4 bytes, object so far. So that's why we make decision. We're working something Dbdk natively, and can support all those things and satisfy our user case. I think that's the most important part as well. Yeah. Hopefully, I answer your question.
Any other questions for Liang?
Hi. Managing memory, no matter how you turn it around, is expensive. You'll need to consolidate the chunk. You'll need to deal with fragmentation. So even if you have some things you do know, like a set of sizes you're running on, or maybe a cache for certain something, the management is still expensive, and there is always overhead. Okay,
I got you. Yeah. So I think what you want to say is external fragment, right? So
I actually mean that. Why do you think that the correct solution is accelerate something which always takes calculation? So why not relying on pre-allocations and reusing those pre-allocations?
Okay, the pre-allocation like a memory pool. The memory pool pre-allocation just cannot support flexible total size and unit size. For example, you create a memory pool with say 400 meg. That's it, right? You need to run this until to the end. So we need a more flexible design, and definitely you need to pay price. I get your point. You say all this kind of metadata and the control structure, that's the price. Yeah, but you gain the flexibilities. And also you see for certain application like a user space protocol stack, they really need the flexible sign as well, and not just us. Yeah, thank you.
Any additional questions or thoughts, insights for Liang? Okay, well, thank you so much for
thank
coming.
you. Thank you
coming
very
and giving a talk. Really enjoyed it. Great. So the next item on our schedule, we actually have a break right now that's coming up, and I'm going to give you the right information. Yeah, the break actually runs from officially from 3:10 to 3:25, so feel free to go out, get a snack, you can come back, and then we have a few more talks today. Well, the first will be a template and asynchronous API abstract from Arcachon and NVIDIA, and that begins at 3:25 p.m. So we'll look forward to seeing you back then. Thank you.
Yeah. Thank you. Thank you very much.
I think we're about ready to start again. We have Ori Karn from NVIDIA here to talk about templated asynchronous API abstract with Dpdk. So I will turn it over to Ori now.
Hello, everyone, and thank you for having me. Today I'm going to talk about the RT flow template API, which is a new introduction to the RT flow, basically. Okay, so some word about myself. My name is Ori Karn. I have over 20 years of experience in development. 6 out of them are in the Dpdk community, and I'm the RT flow and regex maintainer. The outline for this presentation is basically a bit about the history of the RT flow, what we learned when we worked in the RT flow template API, which was introduced last year, and some how-tos and tips to better utilize your application to use it and to better develop for it. In this graph, we basically see that in the x-axis, the years, while in the y-axis, we see the number of flows that the application requests to insert. As you can see, from 2015 to 2018, the application didn't request much flows. They were basically just control flows, match on ETH/tag, do RSS, and drop, that's it. Later on, application decided to request more actions, more items, number of flows increased. By 2021, we reached to around 1 million flows/rules per application. And by 2022, as we can see, a dramatic increase, which basically application wants to insert over 16 million rules. Actually, it wants to insert 16 million connections, not rules. And each connection it's at least bidirectional, so it means like 32 million rules, even more. So as we can see from relatively steady state with handful of rules, it was translated to many more rules, and in very, very short time, it was translated to millions of rules. So how did it become so? So like I said in the beginning, it was very simple rules, just control flows, match on Mac, match on VLAN tag, do RSS, do drop, that's it. Then a request comes from the application, we want more flexibility. This was the time RT flow was introduced. It was introduced when there were no rules and basically tried to give better control, better flexibility to add rules to the applications. The rules were still designed to be controlled, but there were supposed to be many more rules and more flexible. So the idea was, and it was proven that it will be easy to add new items. We cannot foresee which item the application will request. We cannot see which actions. So as long as the hardware can support it, we can expose it to the application. As we can see, it proved quite useful. So between 2018 to now, RT flow action grew from around 10 to 50, and the items moved from about 20 to more than 70 different items that RT flow currently support. But during this time, basically, it was designed to be synchronous. It designed to be part of the control path. It was now designed to be multi-threaded. Again, the idea was the flexibility and to expose the hardware. By doing so, it basically opened the gate. And this gate basically allowed the application to offload rules, and they saw the light. So basically, by seeing the light, they wanted to insert much more rules, and much more than just control. And instead of controls, they moved to packet-driven or to data-driven rules. So a new era arrived, and basically, we needed something that scales up and gives the flexibility of the RTE flow, but also allows much faster insertion and support. So this is how we decided to implement the RT template API, which is basically additional API introduced for the RT flow. It was designed to be asynchronous by nature. It was designed as multi-threaded and almost no resource allocation. As previously stated in just the last presentation, malloc and everything is costly. Everything that should be done per rule, it's better to do it in advance. It will save time. Everything has a cost attached to it. So this is what the template API will try to solve. Sorry, it doesn't work. Am I missing something? Oh. Okay. So just to show the improvement. Basically, in this graph, on the x-axis, we can see the number of threads being used, while on the y-axis, we see the number of rules being inserted in kilos. So basically, if I'm looking at the one thread, the blue is the new template API, the red is the standard API. We see that in the template API, we managed to insert 1.3 million rules per second, while in the standard API, we are enabled to insert only 150K rules per second. A huge increasement in the template API. Additionally, what we can see is that between one thread and four thread, that the standard API moves from 151 to 160. We added 4 cores, we only got 10K or more rules to insert. While if we look at the template API, we can see that it scales much better, from 1.3 million to 2.4 million almost. A huge increase. I admit not linearly, there is limitation, but we still see a huge scalability. Basically, so we can see from this graph that the new template API is 10x faster than the standard one. One of the key aspects, like I mentioned before, is that the template API is configured except asynchronously and everything else, also between control and data path. Everything we want to allocate is in the control path, so while you're inserting the rules in the data path, there will be no allocation and nothing will be created new. So in this case, what we can see is that both of in the x-axis, we see the thread, in the y, the number of flows, the number of rules. Both of them, blue and red, are the template API. The only difference between those two is basically that we are saying, I want to insert 8 million rules, basically, with mark and RSS. We have 8 different RSS. But in the blue one, I'm configuring the RSS in the template. So it means every rule that uses this template will get the same RSS. And I'm simply creating 8 templates. While on the red, which uses the RSS, still 8, but I'm inserting the RSS when I'm inserting the rule. That's the only difference. We can see 21% improvement using the fixed action. Again, it's exactly the same. The only difference is if I declare in advance that I'm going to use specific RSS, or I'm letting the application, letting the PMD during rule insertion test if this RSS exists or not, or if it needs to be allocated or not. That's the only difference, and it's already increased our performance by 21%, which is, I think it's a huge number. At the end, offload, basically, the target of the application is never to offload rules. Offload rules is the means, it's not the end, it's not the objective. Applications is designed to do something with packets, process packets and do something with them. The idea of offloads is that if we can offload and we can save the application CPU, time, allow it to do more, it's good. But as long as the application is basically doing partial offload, which means that it still answers the packets, it means that the application does 2 things. First of all, insert rules, and does the packet processing. So each CPU cycle that we take in order to insert rules means that it's less the CPU cycle that it has to process the packets. So in this table, I'm basically showing that the difference that the new template API almost takes no CPU cycles from the software. How do we see that? The first line, basically, we see a single rule. The single rule means that application just insert RSS and everything is handled in software. The second rule, the second line basically means application insert a rule per connection. The rule just marks the packet and does RSS. That's it. So basically, we are saving the application the ID of the packet. As you can see, the throughput is about the same. The CPU, with a small, neglectable throughput, and the CPU is the same. With this, sorry? Sure. Sorry. Thanks. So basically, we can see that given the same CPU percentage, managed to do the same throughput both without offload and offload. This means that the cost of offloading a rule, the application didn't notice it at all. This is a very big thing, because until now, there was all the questions, is it worth to offload the rule? Now we see that it doesn't cost. Just to make my point even more, to emphasize my point even more, is that you can see here the comparison between the template API to the standard API. We have around 44K rules per second, and we see that the CPU cycle, I will start from the right, basically increases when we use the standard RT with about 4%, 3% actually. But more importantly, we see that the throughput drops from 48.5 to just 15. This means that the application, instead of processing those 48 gigabytes of bits, it was invested in offloading rules. This is not what we wanted. This is not the objective of rules. So basically, we can see that using the old API, not the old, standard API, basically the CPU and the application is involved in certain rules instead of doing what it should be doing, packet processing. Okay, so I hope that I showed until now that the API is good and it's nice and everybody should use it. But how do you use it best? How can you leverage your application? How can you leverage your code to use it? First of all, you need to understand that you need to learn your application. Just like any good developers here, I guess, and when you come to design a new feature, you're preparing, you're learning. So here you also need to learn about your application and probably need to modify it. You cannot take an application as is and use it, because you need to know what you can pre-allocate, what can be set as fixed, what must be kept as dynamic. So you need to learn the application and probably modify it. The second point is always use pre-allocated resources. Again, everything that you allocate during rule creation will cost you. Third point is interleave between hardware and software. The hardware works in parallel to the software, so you should avoid at all costs the things that software works, and then hardware works, and then software works, and then hardware works. Basically, you're not utilizing the hardware. The hardware has the beautiful capability to work in total parallel to the software. So if the software works, also the hardware should work at the same given time. Last point that I want to make in this slide is basically every resource it counts, even the smallest, even what we think is neglectable, everything at the end is counted. We are talking about hardware, the hardware is limited. Limited resources, limited memory, cache misses. Everything that happens should be calculated for and justified. Everything here is nice, but how do you implement it? Let's look at that way. Let's see how can be implemented. So in order to do that, let's take a simple test case, 5G VNF application. Basically, it's partially offloaded for each connection. It needs to offload two rules, one Rx, one Tx. In the Rx, we are matching 5 tuple, doing decap, mark action, and queue. For the Tx, we are matching the 5 tuple and basically doing encap. The encap is per session and not per connection. Number of sessions in the system is 250K. Number of connections is 8 million. Each session is actually built for number of connection, so that's how we get it. Connection is a user basically, and like you know, every one of us here is basically much more utilizing. It's not just one connection that you're opening a lot more. Okay, so what can we do to improve? First of all, like I said, everything we should consider is pre-allocating. So as we saw from the Rx, basically we have the decap, and then we have the mark and the queue. Decap is the same for all. Basically, we're just trimming the packet. It's not flow dependent. So let's do it fixed. Let's move it to the template API. Secondly, we have the mark. Mark can't be helped. It's per 5 tuple, must be kept as dynamic. Queue Queue is interesting. It's per 5 tuple, but we have only like 8 queues. So we can use the RT flow handle and pre-create the action queue and simply reuse this action instead of, for each flow, insert queue action. So already we are basically moving from fixed, which is best, to a pre-allocated, the action handle, to the last one, which marked, which we cannot be avoided, which is dynamic per flow. Like I said before, we need to interleave. So one way to do it is, for example, Rx burst and then running on all packets, and for each new connection that we want to offload this connection. Insert TX rule, insert Rx rule, busy wait for completion. In this case, while we're inserting the rules, the hardware doesn't work. We want to achieve the interleaved. Basically, this can be achieved by using bulks. So basically, if I'm doing the same thing, Rx burst 256, I can say that I'm analyzing the packet only after 32 rules being inserted. I will push them really to the hardware and then poll for completion. Again, not busy wait, just see if I get completion and move to the next bulk. Basically, by working on the next bulk, the hardware works already on the previous bulk. So when the second bulk is complete, I will get a result from the hardware for the first bulk, and so on and so on. So basically, the hardware works in parallel. Every resource is valuable, and this is a bit tricky. Until now, it was relatively straightforward. Like we said in the TX, we want to encap. The encap is basically based on the sessions. We have only 250K session, while we have 8 million rules. What can we do to save this? So this means that we need 250 different encaps. So we can, in the naive way, create 8 millions and just reuse the encaps. But this means that we use the action, we pre-allocated everything, but we still inserted 8 million and we still wasted memory in order to hold all those rules. A better approach, a much better one, will be say, okay, I can, instead of match on 5 tuple, and since it's partially offloaded, the application can give me a metadata to say, okay, this flow belongs to some session. So basically, I don't need to match on 5 tuple, I need to match on a metadata supplied by the application, and just based on that, do the encap. This will result in that it will be very easy. There will be only 250K rules, each one is different encap, and we are simply matching those encaps. So much less resources are wasted. Okay, and a quick recap. The template API is much faster, it's 10x faster than standard RTE flow. Keep that in mind. It's scalable, meaning we can use it in multi-cores. Unlike the standard API, which is locks and everything, the idea of this API is to be used as between cores and multiple cores. It's data-oriented. We care about the data. Everything that is written in this API is data-sensitive. But it also means that in order to fully utilize it, you must understand your app and you must modify it. It doesn't work if the application doesn't match it. If, for example, you cannot know everything and you're doing everything for each flow, you will not get any benefit. The idea is what can be known and what, even if it's just part of them, it's good to have anything. And in any case, you need to think about maybe making changes to your application. The last thing basically is a call for action. You need to say, okay, first of all, from the driver manufacturers, add your driver. As long as one of the key points that make the RT flow so widely used is everybody's contributing to it. So please contribute, add your PMD to it. Secondly, from application developers, add your application, make the changes, show example to other applications how it should be. For example, OVS is a use case. Everybody's learning and basically copying or duplicating the OVS and just making small changes. So if we do it right, everyone will copy the correct things and get a better performance. Questions?
Do we have any questions for Ari?
Thank you. Hi, so I've got one kind of complex question about the asynchronous nature. So there is a typical problem with this creating flows which are offloaded by hardware is by the time the packets, you receive the packet, you want to create a new rule, there are already dozens of packets waiting in a DMA queue. They should be, let's say, from the same rule. So once you send the rule to the hardware, it takes some delay. By the time it reaches the hardware, you've got another couple of dozen of packets which haven't been processed by the rule because the rule didn't get there, right? And now you need to figure out, okay, so I received the same packet, but I already sent the rule, so I need to keep some kind of a cache or whatever to memorize that you sent already the rule, or you just forget it and send the rule once again. The hardware has to figure out that you duplicated. So how do you solve this issue?
Very good questions. Very, very good questions. We encountered it, this scenario multiple times. Basically, it's depending on the application itself. Because, for example, there is application that says, okay, I prefer to insert the rule prior to the hardware because, for example, it's quota or it's meters. So it's important for me that the hardware will count everything. So I cannot skip. So basically, it means that I may re-inject the packet. I know this packet will be delayed in latency, but it will help me keep the hardware and be synchronized. And the quota will be correct, and the counters will be correct, and everything will be correct. So that's one way to re-inject the packet. Another way is, just like you said, keep it in the side until the flow is offloaded and only then pull, which will result in increased latency, but maybe that's the best solution for your application. And lastly, you can, if you don't care about hardware synchronization, you don't have quota, for example, and you care about latency, you can always say, okay, I'm doing everything also in software. I have the software pipe. Hopefully, the software pipe will be used only for a limited time set. But I can still, so it's very dependent on your application. Everything is supported, and like I said, you need to know your application to decide the best solution.
That use case you described, that's like a typical use case of an exception path, right? So part of the flows are processed in software, then they gradually become offloaded in hardware, but you need to like sync the state between those two. Okay, I get it. Thank you.
Yeah, connection tracking, for example, everything like this, that's a must. So that depends.
Okay, thank you.
Sure.
Do we have any other questions from Ori, either at home? You can put them in the chat or anyone physically here. Any thoughts, insights, etc.?
Thank you, guys.
Okay, thank you very much.
Thank you.
It was great. Really appreciate you coming down. Okay. We have, I think on time it's, let's see, we're at 3, we're a little early, but I believe we do have Lucas Sismus here. Lucas, are you on site? Yeah, we can go ahead if you're ready. I'd like to introduce our next speaker from, I'm giving you the right info. Lucas Sismus from CESnet, here to talk about accelerating Dpdk with Suricata.
Yes. Hi. All right. Hi, everybody. My name is Lucas Sismus, but you can leave out accents and just call me Lucas. I'm a researcher at CESnet primarily, but I'm also a PhD student and newly a team member of Suricata. In my work, I primarily focus on accelerating Suricata with Dpdk. So today I would like to tell you more about what Suricata actually is, then tell you the state of Dpdk in Suricata, how we use Dpdk in Suricata, and then present Dpdk prefilters as an alternative to even further accelerate Suricata using Dpdk. All right, so what is Suricata? Suricata is a community-driven, meaning open source software which monitors networks by extracting application layers, events from application layers, which could mean that it extracts HTTP logs, it extracts TLS keys, I mean, payloads from HTTP, let's say, and logs it to a central place. Then it does signature-based packet analysis, which means you have set of some rules, and they are used to inspect the passing through packets. Suricata can be as a passive receiver, meaning it receives only copies from the network and doesn't interrupt the traffic flow itself, which is called IDS setup, intrusion detection system. It can read PCAPs, or it can be directly placed in the wire and inspect all the traffic that's passing through, and that's intrusion prevention system. This intrusion prevention system then can have rules to block the actual passing through traffic. By default, it has the general GPL v2 license by OSF. That's the organization behind the actual Suricata. To have a better idea where we can place Suricata is, well, you are usually a network administrator, which you manage some network and you place it within that network. And you either place it there as a IDS setup or IPS. That's up on you. And from Suricata, you then have outputs for, like I said, from the app layer events, meaning network security monitoring application. Then it analyzes packets with signatures. It can extract the payloads. Based on rules, it can, for instance, record PCAPs of when some condition is triggered to be able to analyze the traffic later on. Suricata itself has multiple modules which it consists of. As you can see on the right-hand image, you have packet capture module, packet decoding module, detection and output module. But for Dpdk, mostly the most interesting module is the packet capture module, of course. It already contained a few modules like AF packet, NFQ, PF ring, and some others as well. And part of my master thesis, I implemented the Dpdk capture module. It's been already merged in the main branch, and will be already part of Suricata 7.0 release, which is due to be soon. But that can be already Suricata can be already compiled with this capture module. The module I implemented works in a primary process mode, and part of my Suricon talk about this implementation, I made a performance graph, which, as you can see, was presented on a Suricon conference. The horizontal line describes the transmit speed, and vertical lines describes percentage of dropped packets, meaning how many packets were dropped versus number of transmitted packets. The measurement had two variants. The blue line basically describes the most popular capture module, which is the AF packet, the most used one. And the orange line described the Dpdk. There were 16 threads of Suricata running on each test case. And as you can see, the Dpdk outperformed AF packet. From my measurement, it outperformed or helped Suricata by about 10 to 15%, then increased the throughput. By other measurements, I I was able to see and heard from other community members that Dbdk also improved latency quite a bit. So currently, Dpdk in Suricata provides support for primary process mode, which means, and was tested by me mainly on physical NICs running on physical machines. I didn't try it in virtual functions and stuff like that, but so far it was, I'm keeping it physical. But then I implemented the capture module, but then we were like, what are the next steps? So usually you can either improve the processing speed of the actual application of Suricata or limit the amount of traffic passed to Suricata. With this in mind, we came up with Dpdk pre-filters, which is, let's say, architecture in new architecture in Dpdk environment, where we use primarily the features of Dpdk such as primary and secondary process, where we have some Dpdk pre-filter in front of Suricata that can filter the incoming traffic, which means the traffic that we are passing through Suricata might be filtered even before Suricata knows about it. So you can, let's say, insert a rule to the Dpdk pre-filter to only filter traffic from this IP prefix, and Suricata doesn't really need to know about this. Then it can also provide a synchronous flow-based bypass, and that's driven by Suricata. So Suricata inspects some flow and tells Dpdk pre-filter, I don't want to see this flow anymore, and Dpdk pre-filter will handle this. Or Dpdk pre-filter or the NIC can add metadata to packets that are passing through these systems, basically. I have this in a diagram as well. If we look at the diagram, we see on the very left the NIC that's receiving packets. And then it leads, there is an arrow and packet leading to the Dpdk pre-filter, which basically receives packets of all the NICs that it works with. And this Dpdk pre-filter is running as a primary process, which means that Suricata must run basically as a secondary process. And that means that requires us to implement the secondary support. So Suricata now has already secondary support. This connection was done using Dpdk rings, which means that Suricata does not need to bother with setting up the devices itself, and only connect to or attach to the Dpdk rings. So this work also provides stable vendor-neutral Dpdk ring API, which uses Suricata to get packets. And as you can also see, Suricata can also out packets. That's for IPS setups. So that's also supported in this work. And the last point in this diagram, we see that it supports non-blocking bypass stats update. When Suricata tells pre-filter that I don't want to see this flow anymore, it still wants to see how active the flow is. And if it's still active, it wants to get at least the stats of the flow. So it periodically asks Dpdk pre-filter for these statistics. And that's through the bypass channel that you see in the middle between Dpdk pre-filter and Suricata. Now, you also see the meta fields there, and that's basically support for metadata. that can improve the processing speed of Suricata itself or other parts of the whole architecture. Basically, the bypass method or the filtering method help to limit the amount of traffic passed to Suricata, but metadata actually supports or are supposed to improve processing speed of Suricata to reach better performance. Now you see that NIC can add metadata to the packet, but Dpdk prefilter might have different heuristics to add different metadata to the packet itself. So that's why on the packet between Dpdk prefilter and Suricata, it might contain a little bit different metadata than what are passed from the NIC itself. We can take, for example, Dpdk prefilter might contain some machine learning module, which could add another set of metadata to the packet itself. And then when Suricata is finished with the detection and sends packets back to the Dpdk prefilter, it might also want to add metadata on the way to the prefilter, so that the metadata are used by prefilter to better to improve, let's say, the machine learning module. Since Suricata is able to run as a secondary module, there are also other use cases for how these Dpdk applications could be set up. Apart from the usual, the basic module, the basic deployment architecture, let's say, that's pretty straightforward. It can basically read data or packets from different application that's before the Suricata, and then pass it to the other application through Dpdk rings as well. Or Dpdk prefilter might serve as a kind of distributor between Suricata and other application that would basically use another features of Dpdk, so that packets don't need to copy to these different applications and only are read by both applications. This basically means that within one server you can have multiple Dpdk applications that are connected together. But so far we primarily focus on this simplified concept with only Suricata and Dpdk prefilter to reach the highest throughput we can. So I've presented the whole concept here, but what's currently implemented and what's in progress is summarized in this slide. Basically, the Dpdk prefilter and Suricata itself needs to kind of synchronize together. And for that, we have inter-process communication. We use the Dpdk IPC API to, let's say, for Suricata to attach to the prefilter, to tell prefilter that I want to stop receiving packets and so on. Then you need to also share configuration between Suricata and prefilters, as prefilter initializes all the stuff and basically it passes down the resources to Suricata. And then prefilter, although it is shown in this diagram as in 1-to-1 ratio, Dpdk prefilter can work as a single core and distributing to multiple Suricata workers. And on Dpdk prefilter, one core of Dpdk prefilter can work with multiple NICs as well, the multiple ports of the NIC. Which means that the cost of Dpdk prefilter or adding another core to the overall architecture is basically amortized over the whole architecture. The packet distribution works in, as I mentioned, in IDS and IPS mode. And there are message channels between Suricata and prefilter to exchange messages for the asynchronous bypass, for the bypass update, and so on. What's left to be done is are the packets metadata, in which we would improve Suricata's processing speed. But that's to be planned, also to be stored within the RTM. So here it might be a little bit more complex view on the overall architecture. As you can see, that you have one prefilter core which distributes traffic to multiple Suricata workers. That's SW. And these workers basically are the ones that process all the packets and go through the detection analysis. From all the threads, you have message rings, which can basically mean that these threads can send messages that I want to bypass this flow, and so I don't need to see it anymore. And flow manager, when the flow is bypassed, sends message to the task ring or to the prefilter to get new statistic about bypass. Because even though the flow is bypassed, it's still stored in the Suricata flow storage. And then when prefilter gets the information that Suricata wants based on the message it received, then prefilter basically responds to the flow manager assistant, which sets the correct, let's say, statistic of the bypass flow in the flow storage of Suricata. In the upper layer, we see the inter-process communication for synchronizing states between the two systems. And we also see the configuration memory zone for sharing the initialized resources. As I mentioned earlier, there is only one NIC displayed, but the Dpdk prefilter can actually work with two, let's say, ports, so that it works in the IPS mode as well. Here are the kind of responsibilities of one prefilter core, basically what it does in its one cycle, and that's receiving packets of, let's say, both NICs, bypassing packets, distributing packets among Suricata workers, and getting messages. That's dequeuing task ring, processing these messages, and replying to Suricata, basically. This architecture, as I said, is already kind of implemented, and I did some early tests on how it's doing. And for test, I used Suricata machine that had Intel Xeon. My setup was based only on one NUMA node, so I only used one of the CPU. I used NVIDIA Connect X5 card for this test. And basically there were 8 Suricata workers enabled. The replayed PCAP had average packet size of 750 bytes. And it was replayed at different speeds to see how Suricata and how the whole system behaves, basically. We see the first graph, which, as I mentioned, has 8 Suricata workers enabled. So there were 8 threads receiving packets. This was this was a comparison between the standalone Dpdk Suricata, that's red line, and Dpdk prefilter plus Suricata, that's the new architecture. And basically the standalone Suricata is the, well, as you might have seen, the most performant, I would say, capture module for Suricata, and that's why I chose this variant basically. And in this graph, we see the horizontal line which describes the transmission speed, and the vertical line describes the percentage of received packets. And this graph basically shows that both variants start to lose or start to drop packets at let's say about the same speed, even though the pre-filter variant is a little bit better. But this is basically because Suricata, in this case, in this test case, was running with emerging threads open. That's a rule set which is publicly available. It's quite big and quite heavy for Suricata, but it doesn't contain many bypass rules. Suricata basically with this rule set inspects still most of the traffic. There are instances where Suricata might trigger bypass by itself, but it wasn't set up like this. So in this test case was mostly focused on just receiving packets and proving that Dpdk pre-filter doesn't really worsen the actual performance, but it's only there. But the main help in this architecture is basically in when you bypass a lot of packets. In this use case, I also used the emerging threads open rule set, which was quite heavy, but I also added 2 rules which bypassed encrypted TLS 1.2 traffic when it was encrypted. So at this point, when the traffic is encrypted, Suricata doesn't really know or is not able to do much more than to receive and dump the traffic anymore. So these rules were able to trigger the bypass. And it shows that the red line, which describes the standalone Dpdk Suricata, reaches 8 gigabits per second on 8 Suricata workers, while the architecture with Dpdk pre-filter reaches 11.6 gigabits per second. And that's close to 3 gigabits improvement, which is quite a lot on 8 cores. To see how big improvement it is, I've also recalculated these numbers to per L-core basis. And that's shown in this graph, where the blue column describes the standalone Suricata, and the red column describes the Dpdk pre-filter with the Suricata. The vertical axis describes the speed per core, where standalone Suricata used 8 cores and Dpdk pre-filter plus Suricata used in total 9 cores. So this was taken into consideration, but still, even though the Dpdk pre-filter used 1 core more, it still provides 15% increase in performance, which sounds really nice, considering compared to AFPK, Dpdk alone proved 15% increase, and then this also brings another 15%. But I mean, on different use cases, it can bring even more or less. It depends on the use case as well. This was a kind of short intro and to give you an overview. But if you walk away from this room, I will be happy if you remember that Suricata is basically an engine that either monitors network traffic and extracts the application layer events. It logs what's happening on the network, analyzes packets against the set of rules, and already contains Dpdk. So you can also start experimenting with Suricata. And the new architecture, Dpdk prefilter, provides the new Dpdk ring API so that Suricata does not need to be bothered with Rsa's configuration, which we know it's different between devices, other types of configuration which might be a little bit hard to maintain for Suricata. It can also provide synchronous traffic bypass so that it doesn't need to really lock or stop at anything. It just sends message to the Dpdk prefilter and asks for update of the bypass flow. And it also provides custom metadata that will hopefully soon be implemented, and we will test it out how it works.
Lucas, we have a question here from our lead maintainer, Tomas.
So just thank you, and I would like to just tell that I would be happy to see you all at Suricon in Athens this year. And would like to thank you, my faculty, Cessna and Suricata team for the support. And the last slide contains all the links that you might be interested. Dpdk prefilter, which is currently in version 4 and on my branch. The Suricon talk from the last year and Suricon, this year's Suricon's page. All right. I'm happy to answer any questions, and we'll be happy for feedback.
Yes, please. Why the prefilter you're using? I don't understand the idea of prefilter. I do understand, but why use ring and not RT-flow, basically?
Why is Suricata not using RT-flow?
No, why you're using rings? Why rings and not RT-flow?
I mean, I take RT-flow as hardware acceleration, whereas we wanted to have a place in front of Suricata that's easy to modify, and you can basically put any kind of experiment within the Dpdk prefilter and not worry about Suricata code base, because it might often get quite complex. And that's why we wanted to put kind of just a layer between the NIC itself and Suricata. And Dpdk prefilter can then either manage their own kind of offloads or filtering, bypass, and if it wants to use the RT-flow, then Suricata just can send a message, and Dpdk prefilter will take care of that, basically.
Let me rephrase my questions. Dpdk prefilter, okay, but you don't need the ring between the Dpdk prefilter to Suricata. You don't need RT rings, that's what I'm saying. Dpdk prefilter can do everything that you said, that's okay, but you can use RT-flow instead of rings. Query the queues. Yeah.
Yeah, do you mean like the Dpdk prefilter would configure the RT-flow to receive packets? Or would the Dpdk prefilter would configure RT-flow to forward packets from the Dpdk prefilter to Suricata?
No, directly from. So the prefilter basically will send traffic that the Suricata wants from the NIC to RSS queue on the Suricata. So instead of the Suricata polling on software queues, it will work on hardware queues. That's the only difference.
Yes. I mean...
yeah, I'm just thinking, never mind.
Okay, a different question. So first, thank you for working on Suricata. That's a very old story. That's a very old story to have Dpdk on Suricata. I know that others before you tried, and the maintainer were not satisfied with the result. So, are you working with the maintainer to make sure it will be integrated?
Correct. as I mentioned, I'm newly a Suricata member itself within the team, so I'm closely working with the Suricata team to maintain basically the Dpdk within Suricata.
Okay, great. So you are going to maintain this part in Suricata yourself. You are committed.
Yeah, it looks like I will be the main maintainer so far of the Dpdk.
Okay.
Yeah, thanks for the talk. Another question regarding the forwarding between the various stages you showed on, I think it was the next slide. Yeah, exactly there. So you said that you use Dpdk IPC there, but I mean you have a lot of limitations when using Dpdk IPC, and why not simply integrate everything in the Suricata application itself and use a plugin infrastructure there, but then running everything in the same process?
I mean, from my point of view, the IPC I didn't see IPC limitations, and I just wanted to use it for synchronizing states. It's not used in when packets are received. It's not used when messages are exchanged. But the IPC is just a general platform to let's say, attach Suricata to the existing pre-filter or to the existing application, and it's not like performance-oriented.
But in the end, so if I got it right from the documentation, you have to disable Linux kernel address layout randomization to make that work. I'm not sure if that's still valid.
I mean, I didn't need to disable. At least I don't think I had to disable anything. It worked out of the box, basically.
Okay, thanks.
Yeah, one question is, so Dpdk recently introduced the regex dev, the regular expression device.
Mm-hmm.
Maybe you could offload that to Suricata if that's an option, so that we can offload some of the regex pattern matching to hardware. Just as a
Exactly. I mean, we also have in mind that putting pattern matching inside a Dpdk prefilter would be quite nice. I mean, you still have some problems with reassembling and the pattern in between packets, but we'll try to solve it in some way and implement this regular expression matcher inside the pre-filter.
Thank you.
But thanks.
So I have a question. So basically, do you also need, so when the Dpdk filter receives the packets, it attaches a new metadata to the packet, right? That these are information required to Suricata, I guess, to process the packets.
I'm sorry, can you maybe...
Oh, sorry, can you hear me?
Oh yeah, I mean, it's just a little bit on the silent side.
Okay, now I was saying, after that Dpdk filter receives the packets, I can see that there is a meta pf packet, so you have to attach a new subset of metadata to the packet to Suricata to make Suricata work on the packet you just received.
Yeah, I mean, there would be allocated probably the private space for in RTM buff of fixed size, and Dpdk prefilter could take the meta information of the NIC and maybe alter the meta information what are said by the NIC and insert their meta information prior to sending the packet to Suricata.
Okay, so basically the Dpdk filter somehow has to process the packets and work on multiple packets coming in from the network card before providing them to Suricata. Okay.
Yeah. As it is doing the bypass, it needs to basically do the 5-tuple parsing at least, or whatever you configure on how you want to bypass packets. But so far it processes all the packets, and those packets which are not bypassed are then sent to the Suricata. Those packets what are bypassed are either discarded or freed, or are sent to the other interface on which they were received in case of IPS mode.
Okay, now because I was curious to see if there's some room for the GPUs either in Suricata itself for the analysis of the packets for security and inferencing, or in the Dpdk filter analyzing multiple packets in parallel. But maybe we can discuss this offline.
All right.
Lucas, thank you so much for taking the time to speak with us today and talk about the intersection between Suricata and Dpdk.
Thank you
It's
very
great
much.
to have you. Okay, this just about concludes day one I should say day two, day one of the speakers of two. But we have one more speaker. We have our own Tech Board's member, Honapa. I'm going to actually mispronounce it. Nagara Hawley, I don't know if I pronounced that right, with the DTS working group update, and he will be streamed in virtually, and then we'll go to closing remarks from our lead maintainer, Tomas Mangelan. Thanks.
Okay, great. Am I in the meeting now?
You are. We can hear you.
Okay, great. Well, thanks a lot, Nathan. It's a great attempt to say my name. Anyway, yeah, good morning, good afternoon, and good evening to everyone. Today, I will provide some of the DTS working group updates, what we have been up to, and what we want to do going forward. Okay, good. So the agenda for today, I'll give a brief introduction about the DTS working group, how it came to existence, for those who are new to the community and who have not followed about what this working group does. I'll talk about the progress that we have achieved so far. Then, some of the procedural changes that we have talked to the tech board and agreed upon. I'll talk about the work we are doing towards 22.11 release, the future roadmap, and call for action, the very important call for action. Okay, so I'll go through these slides, and then we can do a Q&A session at the end. Okay, so introduction to the working group. So today, there are two testing frameworks in Dpdk. The first one is the Dpdk apps, which is in the app directory. There are multiple applications over there to test Dpdk device abstractions like test PMD, test event dev, and so on. We also have the unit test application, which does the testing for various software libraries. So we see that these applications, they get updated, as and when new features are added, and the community makes sure that there is enough testing coverage there through these applications. And the unit test cases, we can run them automatically as well. So there is enough coverage for the unit test cases. We also have another testing framework. We call it as the Dpdk test suite. This is the framework to automate integration testing. It makes use of the applications in the app directory. It contains test cases that make sure that all the devices that are supported in Dpdk behave the same way. So essentially, it's a framework to come up with a topology with server platforms or SoC platforms with various devices attached to those platforms. And then you can also write test cases. For example, you could write a test case to do end-to-end IPsec testing, for example. Okay. So why are we focusing on the DTS? I was not part of very initial discussions, and I forget some of the discussions we have had. But essentially, what it comes down to the test cases and the features not moving at the same pace. We were adding features in Dpdk for various devices, but the test cases were not moving at the same pace. So the tech board debated about using various test frameworks, but ultimately we chose DTS because it was already in a good shape, and we didn't see that other alternatives were on par with DTS. But having chosen DTS, there were a lot of input from various leads in the tech board that DTS needs several improvements and so on. So the tech board decided that we could create a work group which goes ahead and collects all this feedback and then looks at, hey, what can we do with that feedback and how can we improve DTS such that anybody can go ahead and add a test case. So I took up the responsibility to lead this working group, and we had a very first meeting in April 2021. To discuss what we want to do in this working group. So there were various leads from different companies who joined that meeting. And we discussed about making DTS mandatory. So by that, what I mean is whenever Dpdk patch is submitted to implement a new API for device abstraction, or we are implementing some new features in the existing APIs, there needs to be a corresponding test case submitted along with that patch. So, that would ensure that the test cases and the features are moving along at the same pace. So during that meeting, we also agreed to collect feedback from the community as well. Okay, so this is how the DTS working group came into existence. So what we have done, from that meeting. So we went ahead and collected feedback from the community. There was very good feedback from the community, and there was a lot of feedback from the UNH lab through their experience of bringing up DTS in their lab, what all issues they faced and what can be improved and so on. So this feedback was collected in a document, and at the end of these slides, I have got links to all of these documents and Excel sheets that we have created in this working group. So we took this feedback and then we debated around this feedback, and we triaged that feedback, and we just divided that into two categories. A must-have category and a good-to-have category. So the must-have items are the ones which we wanted to fix, before making DTS mandatory. These were, yes, we need to fix them. Without fixing these, we can't make DTS mandatory. And then good-to-have were some things, which could be fixed later. For example, hey, we need more debugging capabilities in DTS. That's something that's good to have. Must have is something like, what can be a good example here for must have? DTS test cases cannot make changes to the Dpdk code. That's a must-have for us. We want to make sure that test cases don't touch Dpdk code. They use existing Dpdk APIs to do whatever they want to do. So those are certain examples of must-haves, and good to have. Again, the documents that we have, clearly mark that feedback into these two categories. And then we went ahead and identified all the test cases in the existing DTS that were modifying Dpdk code. Some of those test cases, when we analyzed, they needed changes in Dpdk. For example, we made certain changes to L3 forward, example application, which would expose certain parameters that the DTS test cases can make use of. We made certain changes on the Dpdk side, and then we also removed some test cases in DTS side. We thought that we don't need them anymore, and we changed certain test cases on DTS side as well. But there is more work to be done. I think there's at least another 30% of the work that's left to be done there. And then along with the changes, we needed several procedural changes. How does some of the procedures that we follow in the Dpdk community, how do they need to change in order to make DTS mandatory? We talked about these changes in the Dpdk tech board, and we agreed upon some of the changes. So I'll talk about these changes in the later slide. We provided an update to the community in October of 2021 to go over where we are. And we have been providing regular updates to tech board as well, especially when we needed to make certain decisions that needed tech board's input. Okay, so now going into the procedural changes, right? So we wanted to make sure that submitting DTS and Dpdk patches together is a possibility. That becomes a reality. The reason being, the DTS patches will have dependencies on the Dpdk patches. So we wanted to make sure that a single patch series can contain patches for both Dpdk as well as DTS. Okay, so this means that the DTS has to be part of Dpdk repo, and we have decided that DTS would be another directory under the existing Dpdk repo. And all these DTS changes that would be submitted in the patch series would be discussed in the Dpdk mailing list. Okay, this also would require some CI infrastructure changes. So for example, today, when Dpdk patch series is submitted, it goes through some check patch, validation. It undergoes some testing in the EVNH lab, and so on. There are some changes required over there, and we really have not discussed what those changes are, but we think that we can discuss those, going forward. So, for example, things like the DTS patch, it will have its own check patch kind of a script that needs to run only on those DTS patches. Those changes need to happen in the CI infrastructure. So we are yet to identify those changes. Okay. Then the DTS releases would be synced with Dpdk releases, including the LTS releases. This is pretty natural because DTS would be another directory within Dpdk. So all the tagging, branching, bug fixing, would follow the same Dpdk policies. I don't think we need to invent something new over there. And then, backporting of Dpdk patches. So if there are any DTS changes that were associated with those Dpdk patches, those also would be backported along with the Dpdk patches. And then the DTS will be experimental for some time. This will give us some freedom in terms of making breaking changes in the DTS. So it is going to be experimental for some time, and I'm not really sure how long that time frame is, but that's something that we need to look for in the future, depending on how DTS matures in the community. Okay, so we will have maintainers for this DTS directory within Dpdk. Lijuan, who has been who is the current DTS maintainer from Intel, she would be the main maintainer, and then Owen, who works with the UNH lab, he would be the co-maintainer for the DTS. And then I expect that there would be module-specific maintainers for the DTS framework itself. This would be based on contributions. I see that Uri has been contributing a lot for this work. So similarly, if we have more contributors in the future, we would like to have module-specific maintainers, just like what we do today in Dpdk. We also expect that Dpdk module maintainers will maintain respective test cases. By this, what I mean is, for example, ETH dev maintainers will maintain the respective test cases in the DTS, in that DTS directory. So that should ensure that, again, the features that are being added have got test cases, respective test cases available within DTS. So, this module maintainer would become the person responsible for ensuring that. Okay. So now moving on to the work that we have been doing towards 22.11. We did some cleanup on the DTS mainline itself. We used Black and iSort. So these are some of the tools that are used to automatically format the code. They have got certain configurations to choose what kind of formatting you want for the code. So we went ahead and ran these tools on the DTS mainline to make sure that the code looks and feels the same throughout the repo. We also used the Pylama tool, which it's kind of a check patch kind of a tool, which makes sure that the patches that are being submitted are following certain criteria. So we came up with certain criteria using Pylama tools, and we used those and ran that against the DTS mainline, and there were some warnings and errors. We fixed those issues. We have removed support for compiling Dpdk with makefile. Dpdk itself has moved on to using Mason alone. So the DTS mainline supports Mason alone now. And I also talked about removing several test cases. We went ahead and removed several test cases. Like, for example, there was a test case for checking ABI. This is already being run external to DTS, so we removed that. There were some test cases which were running unit test cases. Again, this is being done outside already using Mason. So we removed several test cases which we felt are redundant. We also ended up removing some of the files that had the GPL license, but we are not able to remove all of them. But what we have made sure is GPL files that were there in the framework that are removed, but the GPL files that were there for the test cases, they are still there. But I think we have got a strategy to address that. We will put them in a separate repo and pull them as and when we are running the test cases. But again, those are test case specific, and we will talk about them more when we start integrating the test cases. And not all test cases require these GPL files. Okay, so that's the cleanup work that we did on the DTS mainline, and that cleanup would apply to the DTS that would come into the Dpdk repo. So there were some changes that we didn't want to make in the DTS mainline. We wanted them to apply only for the DTS that we are bringing in, because we thought they are kind of they might break changes in DTS, for example. So some of the changes we did was the copyright header changes. The copyright header, there was a long format. We changed all of that to follow the SPDX format with BSD3. Actually, these copyright header changes went into the DTS mainline as well. So all the files conform to that, conform to the format that we are using in Dpdk currently. And then we went ahead and renamed a lot of base classes to make sure that we have these new definitions that we came up with, and we went ahead and made those changes. But this change is only available in the future DTS branch. So the future DTS branch is the one that we are going to use to create patches out of. By that, what I mean is the patches that we are submitting to the Dpdk community, they would come out of the future DTS branch. They will not come out of the DTS mainline branch. So this means that the future DTS branch needs to be synced with DTS mainline. So what we are thinking is every time the DTS mainline makes a release, we would cherry pick the patches from DTS mainline into future DTS branch. So that way the future DTS is aligned with DTS mainline, as well as it is aligned with the patches that we are sending into the Dpdk community. Okay. Sorry, just give me one moment. Okay, good. So now, so that's the work that we did in the DTS mainline and the future DTS branch. Now, we were looking at how do we start creating patches that we can send to the Dpdk community. We kind of, needed some direction and feedback from the Dpdk community on that front. So in our first attempt, we just took the DTS framework and we kind of sliced and diced it around certain boundaries. The sole goal we had over there was how can we make it easy for the Dpdk community to kind of review this DTS framework, right? And it was very important for us to ensure that the work that we are doing, that the work that we are bringing into Dpdk community is reviewed and agreed upon in the community. So we just had the sole goal that, hey, let's just take this framework and try and see how we can make it easy. So we just went ahead and broke it around certain boundaries. And it was not a clean separation just because, now we are taking this code that has been developed for a long time and we are trying to slice it. So that was a very what to say, kind of a brute force attempt to send those patches, but we received a lot of good feedback, and that made us think through as to how we want to achieve this. So we received feedback from Samad, David, and others in terms of what they would like to see. They wanted to see patches in small quantities. They don't wanted to take this entire framework in one shot. They wanted smaller group of patches, and the patches need to be around functional boundaries. You know, for example, the example that was mentioned was, hey, can I have a patch series that just looks at how can I connect to a DUT, for example, or a SUT, right? So this required us to think through a little bit, and it requires us to make more changes than we anticipated to provide that, cleaner boundaries, which is okay. We think that that's okay. So I think, we think we have a process, we have a way to do this. We think we are very confident on that. So in our second attempt, we have sent 2 patch series. The first one is SSH connection to a SUT. How do we establish a connection to a SUT and run some commands, execute some commands on that SUT. So the first series just is about the basic functionality that we want to achieve. And we are fairly confident here that we have considered the feedback from the community, and we think we are headed in the right direction. But again, we need that feedback. We need the community to look at this, at these 2 patch series and ensure that yes, we are in fact on the right path here. Okay, so we have established a goal for ourselves that in 22.11 we want to merge these 2 patch series. These 2 patch series would ensure that we have a controller node on which the DTS test cases are running, and then we have a SUT which can connect to this controller node, and we can run the hello world application that Dpdk has, and then collect the results back and validate that yes, in fact, the hello world test case ran on the SUT and the results are good. So we think this is a very simple test case, and it should give us basic framework that we can build upon in the future. Okay, so currently in the community, there are 2 patch series. One is the SSH connection series. This has the least amount of code to connect to the SUT. I'm just talking about the highlights of these patches, but you can always go to the patchwork and look at these 2 patch series. So as part of the SSH connection patch series, we are adding some developer tools and project tools. Developer tools are like, I talked about Pylama, which is like a check patch tool. And then we have got, things like Black and ISOT, which developers can make use of as well. We also have got some project tools and various configurations that these tools need. We are managing the dependency using Poetry, so there are some configurations related to Poetry available there. One of the big changes that we are introducing, again, it came from the feedback that we received, is the config parser. We see that in the DTS mainline, the configuration parsing is not very ideal. So we are kind of streamlining that parsing, the config files. And then, once you parse, how that parsed data is distributed within the framework, as well as to the test cases that are that will get added. and then there's a way to validate that configuration as well. This validation is going to be done upfront. You don't need to run test cases to realize that, hey, there's something wrong with the configuration. And the configuration files will follow the YAML format. So this is one of the big changes that's coming in, and I think this is one of the good changes that we will bring in. This also has got the base node class with just connect and execute methods. But we think that this will, there will be more methods added in the subsequent patches. So that's one of the themes that we are adopting, that not everything would be available upfront. Things will be added in an incremental fashion. For example, the config parser, it would be added in an incremental fashion. And again, the best example I can give you is this node class. It has got bare minimum methods right now. And as we move along, there will be more methods added as and when required. So, we have kind of adopted that approach because it makes it easier on our part. We don't need to write up everything upfront. And then it also makes it easy for the community to review. They know that, hey, there are these two methods, and they can really see that these two methods are being used in that patch series. So there's nothing, additional. Hey, there's this additional method, but we don't see the usage of that method. That should not happen. Okay. And then the second series, it's still in the RFC stage. This would be about running that hello world example application on the SUT. This needs some additional work. It needs to be, there needs to be a cleaner separation in the various commits that are there in the series. But we are working on that, and that would come in. So, like I said, this would run the hello world application and validate the results to ensure that, yes, it ran correctly on the SUT. It also has capabilities to build Dpdk on the SUT. It can configure the SUT for running Dpdk applications, and it has also got things to run a test and collect back the results. Yeah, so there are more smaller things that are available in these two patch series. Please look at patchwork and review. I'm really happy with how long the results that we have achieved through these two patches. But again, yeah, we need to be aligned. We need to be aligned with what the community is expecting. So it's good to, I would encourage everyone to go ahead, review these patches, and give us feedback. Okay, future roadmap. Here, this is not the entire thing. This is about how far we are looking into the future. So right now, what we are looking at is once the hello world patch is merged, we would like to add some smoke tests. So these smoke tests would ensure that the topology of the controller, node, SUT, and a traffic generator is in fact set up well. So if you run this smoke test, it will say, yes, your test setup is working well, they are connected the way they are supposed to be connected, and so on, right? So this would require us to run some traffic, between the traffic generator and the SUT. So we are thinking that we will have this traffic generator abstract class with Api backend implemented. And this traffic generator abstract class would allow us to plug in any other traffic generator. So we are thinking that adding this smoke test would be a good first step to introduce some basic performance test. So with this, we think we should be able to have like a T-Rex backend or any other traffic generator backend for that traffic generator abstract class. So once we add a basic performance test, we feel that it should bring in enough maturity in the framework, and that should allow us to bring additional test cases. So we don't know what those additional test cases are that we bring in, but I would think test cases involving ETH dev with the NIC cards would be something that we would target as the first set of test cases to bring in. So those test cases themselves would require changes because we have introduced things like traffic generator abstract class. We also think we would want to improve the logger. Today it is pretty basic, but we want to have some improvements in terms of how much data that we log from a developer perspective that they see on the screen versus how much we can log in files, which automated script in UNH lab can go ahead and do a lot more things. So we have got some ideas there on the logger. So those things will change, and because of those changes, the test cases themselves would need to undergo changes. So yeah, so this is all about how far we are looking ahead at this point. Obviously, there are a lot more test cases that we need to bring in, and those test cases might require changes, additional changes in framework. So we have not thought through all of that, and as we make progress, I think we will have a better idea, and we will see what can be done, and we will publish that additional roadmap going forward. Okay. So one announcement that we would like to make is we would like to merge the DTS working group meeting with the Dpdk CI meeting. The reason being, we have gone through the feedback that we got. We have debated that, and we think we have identified a path forward. So if I have to say in other words, we have done that heavy lifting part, and now we are creating these patches, and I feel it is better to have, discussions around those patches in the community, in the Dpdk mailing list. So instead of discussing them in the DTS working group. This is going to provide a lot more visibility with the work that we have been doing because there are additional stakeholders who are present in the Dpdk CI meeting, we think that it should attract more people to look at these patches that we are creating in the Dpdk community. But having said that, it also means that the Dpdk working group meeting was every week, but the Dpdk CI meeting is every other week. So there will be less number of touch points for the working group as well, but we'll see how that goes. But as of now, the tech board, the DTS working group, and the Dpdk CI meeting stakeholders have agreed to do this merge. So going forward, I'll set a date, maybe September 15th, or I'll identify a date soon enough to do this merge. Okay. Throughout this process, over the period of last one and a half years, I have been working with Uri, Lijuan, Lincoln, and Owen very closely, and it has been really a pleasure to work with them, and they have made tremendous contributions to this working group. I look forward to working with them, And I look forward for the community to see their work through the patches that we are going to submit. And there have been other people who have dropped into the Dpdk working group meetings now and then to check where we are. They have provided feedback and so on. So yeah, thanks to everyone who have provided feedback for the work that we have been doing. Okay, so now the important part, the call for action. Reviews. We have hit that stage where we are sending in patches, and this is the crucial phase where we need to make sure that we are running and we are not getting blocked. All right. So yeah, there are patches in the community today. Take a look, give them a run. I see that they're very simple to run. So please run them, get familiarized with the code. See if you have got any usability feedback when you run these patches, and provide that feedback. Grow your knowledge as well by following along the patches. Ultimately, all the developers have to develop the test cases. So it's good to make sure that you are following along with these patches. If there are any Python experts, I know everybody have a lot of opinion on how Python code should be written. So please, if you know the best practices, provide that feedback. We would like to make sure we are following those best practices for Python. Then we have the DTS community. Please look at these patches and help us avoid any pitfalls that we have seen, that you have seen in the DTS community. We would like to avoid any past mistakes that have happened. And lastly, attend the Dpdk CI meetings, and there are a lot of opportunities to contribute to creating these patches. So please, yeah, the DTS working group can help out in terms of identifying those areas where you can go off, create some patches. We are very open with that. So yeah, please get involved and see what you can do. Okay, yeah, that's all from my side. I'm open for any questions.
Thanks, Anupam. Do we have any questions from in-person attendees about the DTS working group? Lincoln.
Hey, Hanapa, this is Lincoln here. I don't think you hit on it, or maybe I just missed it, and I apologize, but where did we tentatively plan to document or provide the documentation for all of the test cases too, right? So like the steps that are being taken in like the hello world test or whatnot. Because I think that's an important part of this too, that the testing gets described in terms of like what steps are being taken on the platform.
Yeah. Thanks a lot, Lincoln, for that question. The documentation, there is some documentation today in the 2 patches that we have submitted. At this stage, it is pretty simple just because the patches themselves are simple. But the documentation, again, would be added incrementally depending on the patches that we are submitting. So just like what we do in Dpdk today, right? Any patch submitted in Dpdk, there are test cases, there are documentation related changes, and so on as part of the same series. So we are following the same approach. So yeah, the documentation is going to be part of the patches that we are submitting. And we are looking at generating this documentation in an automated fashion. Does that answer the question, Lincoln?
Yeah, I think this.
Yeah, so we are also coming up with a standard documentation format for the test cases. So each test case would follow that format, and that way it would ensure that we have a consistent documentation for every test case. And we are also talking about adding user guides and like two set of guides. One guide is for the developers, which will help them to make sure that they understand how to set up a DTS environment. And then another set of document which will, address like the testing community. It will talk about how to run test cases and so on. So these are the two documents that we are talking about on top of the documents that we are submitting through the patches. Yeah.
Okay, so another question, Stan Kardak here. From my experience, we've had a bit of issues with the DTS, or actually DTS is very particular about system setup it is running on or testing against, and it goes to either the NICs that are going to be used. For example, there are X520 NICs which have a little bit different device IDs, but they're essentially the same device. And let's say DTS only has a single device ID that it tests against. Other type of particularity is that it assumes that there are, for example, at least 8 cores available on each system. There is no such kind of detection of validation. Is that the case? Or the third thing being that it assumes that there is a NUMA setup, for example, even with a single node, but there is a NUMA running on. And all that was in the, let's say, the Python side of the DTS test cases. Is that something that you're also trying to tackle and kind of rework? Did you think about how to tackle the testing matrix, system versus NIC versus feature?
Yeah, I think that's a good point, right? So I'm not exactly sure about these particular things that you talked about, but we are aware of the problems that DTS had. So for example, we have been talking about DTS using only Dpdk APIs. So by that, what I mean is DTS is not going to be aware of any peculiar things about a particular hardware. It is if I have to give an example, if we consider a NIC card, the DTS is going to treat it as a NIC card. It's not going to be Intel NIC card or a Melnot NIC card and so on. So everything would be done through Dpdk API. So that's something that we have talked about. And then we have also talked about doing things through capability APIs. So we don't want to have things like, hey, can I make a list of test cases that I don't want to run because my hardware does not support certain features. Instead, what we want to do is we want to query the hardware, understand what features it's supporting, and then go ahead and run the test cases that are for those features. So those are some of the things that we have discussed. But yeah, I will take these particular things that you mentioned, like, how many cores are there in the system? Can we just work with 1 core or 2 cores versus mandating that, hey, there has to be a NUMA node or 8 cores and so on. We will take that feedback and see, keep that in mind and see, what can be done there.
Awesome, thanks.
Yeah.
Any other questions, thoughts for Honapa about the DTS working group? Anyone in the chat or anyone in person? Okay, if not, thank you, Honapa, for taking the time to go through DTS in such detail. I know not everyone is familiar with the work that the group does, and it's helpful. I appreciate you taking the time out to contribute.
Yep.
So
thank you so much.
You. A pleasure. I'll turn it over now to Thomas Manjalan, our lead maintainer, for closing remarks on day 1 of talks.
hear me now? Okay. You can hear me. So, I hope you enjoyed this day of presentation. Tell me yes? Oh, no. Yeah, you did? Okay. For myself, I especially enjoyed that we had some questions for almost every talk. And for those who are lucky enough to be on site, we were able to continue discussion in the hallways, etc., enjoy French food, etc. So that's just a small message to those who did not come. Next time, just come. Yeah, I think that's the best value of this kind of conference. We can just discuss and improve things together. So to make it a success, we need a lot of people. So I would like to thank the technical team and everybody who helped with the technical team, Nathan, etc. So thank you, everybody. Now, what we are going to do, I would like to propose to get some refreshment, some drinks, or maybe, oh look, the technical team is awesome. So we are here indeed, and there is a place for us which is reserved chez Pierre. It's in French. Pierre is the name, okay? So just on the right side of the cafe, there is a place for us. So we can just have a drink here if you want, and it's also open for dinner. Or maybe you prefer to first try the sand on the beach that you can see here, or even try if the water is not too cold. So that's your call, but let's meet at chez Pierre, if you're okay with that. And tomorrow morning, we will meet again for another day of conference, but I don't remember the time. But it's all on skate.com. I hope all speakers have already uploaded their slides on skate.com. Should be on PDF format, that's better. And that's it. Any question about the day? Any feedback? No? So, thank you, everybody.
Thank you.